Year 2021 for his research by Ahmed University, Chennai. He kickstarted his career as a junior lecturer and is continuing ahead. He, as a renowned expert, has published 6 journals providing valuable insights and shaping the discourse in his field. Throughout his career, he has been committed to ongoing learning and attending national and international conferences to stay at the forefront of his field. His research experience and publications include various topics like generalization of Pythagorean triples and n tuples, note of Fibonacci series, pseudoprimes, and more. As a respectful resource person, I welcome you to this national seminar on mathematics and the future of sustainable technology, sir. The session is yours. Thank you.
Thank you, ma'am. Thank you for your insight, Prabhu. Welcome all the dignitaries on the dais and up there. Please, Santosh Babu sir, leader of this program. Sir, welcome, welcome, ma'am. Welcome to mathematics and future of next seminar. To all the dignitaries on the dais and up there. Thank you very much for inviting me. So I'm today mathematics and computer science. Already is known for the seminar complete. Like shop online and app and health training and everything. To take another computer, see what makes it here.
இது ஏதாச்சும் நம்ம கனெக்ஷன் வச்சிருக்காங்க அவங்ககிட்ட இருந்தா வரல.
ரீச் ஆகுது. அவங்க சைடு பிரச்சனை இல்லை, நம்ம சைடு பிரச்சனை இல்லை. ஏன்னா எனக்கு கரெக்டாக தான் வருது.
நம்ம இதுல ஒண்ணும் இல்லைல்ல.
எனக்கு பிரச்சனை இல்லை. எனக்கு டைம் பண்ணுவோம். ஆஃப் பண்ணுவோம், ஆன் பண்ணுவோம்.
Responding, ma'am, when I asked this English area or not. Okay, ma'am. Actually, the same is the screen is shared or not? Yes. The phone also. Ma'am, is it okay? Is it okay? Is the screen is shared or not? Just see. Is the screen is shared? Is the screen is shared or not? Hello. So,
We can hear you, sir.
Hello. Hello.
Yes, sir. We can hear you, sir.
Yeah. Sir. Good morning.
Morning, sir.
So welcome to National Seminar. Actually, in your case, some of them using media, shop lines, and different lines. Mathematical computer always interrupt. Here we are a new exciting way. That is the mathematics from the computer. Actually, did you know the underlying mathematics behind basic data computer? What makes it is possible? In this seminar, so I am going to give a brief regarding how the importance of mathematics pertains. So myself, Dr. Murthy, Associate Professor of Mathematics. Here, the importance of mathematics, we can take the foundation of mathematics, how the computer science, the role of computer science, the role of mathematics, today's computer, and real world example. Real. Here, you see, the mathematics is a backbone of computers. Okay. Because in mathematics, it provides theoretical and foundational for algorithms, programming languages, and data structures. Here, if you see in the discrete mathematics, calculus for algorithms and data structures and cryptography, etc., will be going to monitored by the graph theory and combinators. Do you know combinators and complex problems? Here, the linear algebra. How the linear algebra works? In the linear algebra, vectors, transformations, and foundational for representing 3D and 2D. At the same time, for the calculus. Here in the same way, the calculus helps in modeling continuous changes which are understanding rates of charts. See here how the algorithm efficiency is there. Let us suppose to take time complexity and big O notation. You know, how many of you know about big O notation? See here, big O notation is the mathematical notation used to find an upper bound. See here, if you wanted to find n square plus 2n plus 3. So O of n square gives the total complexity of the structure. In the same way, mathematics helps to analyze, measure the efficiency of algorithms. And the computer networks. The computer networks, networking and social networks models which are used by using the graph theory and discrete structures. You know discrete structures is the operation is a subject. It's the shortest problems. And the public key cryptography. Here RSA algorithm depends on number theory and modular arithmetic. You know, RSA stands for Ravasit, Shamir and Adleman. These are the three scientists that formulated this algorithm. At the same time, the third part is mathematical concept for graphics. See here, the mathematical transformations and the rendering and simulations. Here, the transformations are all comes under linear transformation to scaling and rotating and translating, and which are essential for computer graphics. At the same time, rendering. Here, geometry and trigonometry are used to rendering 3D and 2D topics. The 2D screens, sorry for that, including the concepts like projects, lightings and shadings. So we are using the major graph theory and trigonometry. See here, the simulations. On simulations, mathematical enables realistic simulations in gaming. So you know, in 99% are using gaming. So realistic. So while you're playing, you can easy in the sense you can while playing you can enjoy the realistic. And the next one, fourth point is data science. Here the data science, statistical foundations, optimization and deep learning are the three major roles. Here the probability theory and statistics are playing a major role. Here the Bayesian networks. You know the Bayesian networks. Bayesian networks is a structural means one-to-one what we call there is a projection. Projection means there is a link in between. That is a Bayesian network. Optimization, then mathematics helps in fine-tuning machine learning models using optimization algorithms such as gradient descent with relay and calculus linear algebra. Here in deep learning, so we are using matrix multiplication, linear transformation and activation of functions. And if you come to the mathematical now playing, world is playing with mathematics in artificial intelligence. You know, AI algorithm, natural language processing, NLPs and search algorithm decision makings. Here see, mathematics is essential for developing algorithms that mimic human cognition. See here, the neural networks and decision trees. You know what I told previously, the same, it's a decision tree making. Each and a one-to-one interaction, one-to-one interlinks, which are possible. And linear algebra, probability theory, and statistics are used to analyze and understanding the human language in application like speech recognition, translation, and sentiment analysis. See, the search algorithm decision makings are concepts like optimization and logic play the key role in building AI systems that makes decisions, navigation environments, and etc. Here, the role of mathematics in software engineering also is wonderful. How we are managing, that means software is managing mathematics. It's a backbone. You need software testing, you know, the mathematics logic, set theory, and combinatory probability. These are used to different inputs and sensors to verify that software working correctly or not. These are mathematics is the base, the combinatory and probability is the base for testing. Here, the same real world applications of mathematics in computer science is also playing a big role. Here, I can tell you with the 3 examples of real world applications, real world examples. See here, cryptography in cybersecurity. See, mathematical concept and number theory are the mathematical concepts are their number theory and modular arithmetic here for cryptography and cyber security. So I can tell you how it works. See, cryptography ensures the data security over the internet using number theory, prime factorization, and modular arithmetic. Here, see, RSA crypto system is the base on the difficulty of factorization large numbers which are in prime, because prime numbers are very less. So that see how the mathematics is playing here in RSA. If you take 2 large numbers, let us suppose large, if you multiply these 2 to create a public key, the security of this system role on the fact that it's computationally hard to factor the product of 2 large primes. That is the beauty. So it is very sensitive information without the private key. We cannot easily to decrypt without using private key. This is a very important. See how the impact, what is the real impact? Cryptography enables the security of billions of online transactions daily, from pursuing items to exchanging emails, security, etc. I can tell you the second real world example with your permission. Linear algebra and calculus are playing a major role mathematics concept for the machine learning and AI in predictive analysis. See, nowadays predictive analysis is very much important. It's playing a good role, because linear here to get the health issue, by getting health issue before getting into the deep, we can learn, we can get the information by using this wonderful system. See here, linear algebra is playing a major role. It's the heart of machine learning model in health issues. So predictive models are trained on the large database to predict future health outcomes, such as predicting the likelihood of diseases based on patient data. Here the calculus is used to optimize these models, and gradient descent is used to the methods. Here, to adjust the parameters to minimize errors, we are using gradient descent. Here, how the beauty of mathematics is, what is the importance of mathematics is here, the linear regression, which is often used in predictive analysis. The relation between the dependent and independent variables is modeling using the matrices. That means matrices is from linear algebra. What is the real world impact? Machine learning algorithms are already being used to predict the patient outcomes. So automate diagnostic procedures at the same time and optimizing drug development and drastically improving the efficiency and accuracy of healthcare systems. It's a very, very important. And the last one is recommendation of algorithm Netflix and YouTube. Here 80% of people are using Netflix and YouTube. Here for this linear algebra and probability, especially graph theory, is playing a vital role. So these platforms, graph theory, to analyze the relation between the users and movies and ratings, they map out the network of the user proficiency to identify the patterns. Here the graph theory is playing this role. And linear algebra helps to analyze the large database by representing these relations in matrices. See here, what is the probability? What probability will do? Probability is used to model uncertain performance and drastic performance and predict what you are most likely, what you are enjoying, what you wanted to enjoy. It will use the probability. So depends upon the probability, you can get the real world example for this Netflix and YouTube, how the mathematics is playing a vital role here. Here, what is the real world impact? Netflix recommendation system accounts for a significant protection and its view at the same time, with studies showing 80% of people are watching, showing how mathematics helps shape our entertainment with our choices. Here the role of mathematics in advanced future says quantum computing and automated vehicles already came, and robotics manufacturing. See, what I want to say is here, without mathematics, our digital world would be far less powerful. From securing our data to making sense of massive data sets and rendering stunning visuals, mathematics is the invisible force. You can say it's a god that makes computer works. See, finally, I can say mathematics isn't just a tool for solving abstract problems. It is the key that unlocks innovation in every area of computer science. If you wanted to be a part of the shaping tomorrow's technology, understanding mathematics is your gateway to success. What are the key here? The keys are the mathematics is the unseen force behind the technology we rely on every day, and from securing our online transactions and for the future engineers, as a future engineer, computer scientists and innovators, and mastering mathematical concepts will empower you to create solution to some of the world's most precise challenges. And from encryption to AI, mathematical tools are driving advertisements across industries. As the technology continues to evolve, math will remain at the forefront of every breakthrough, making it an indispensable skill for the future. So with this, I can conclude my talk. Thank you very much for valuable time. At the same time, I can say sorry because with some network issues, I cannot attend it for the first and foremost. Right. Thank you very much.
Thank you, sir.
I can thank you, Sangeeta ma'am,
Thank you, sir.
Kavita ma'am. I can thank our principal sir, Dr. Santosh Babu sir, and mostly I have to thank the people who suggested me to give this opportunity. This is signing off, Dr. Thank you very much, ma'am.
Thank you, sir, for your efficient information about the importance of mathematics.
Thank you, sir.
Thank you, ma'am. Thank you, ma'am. Thank you, thank you.
I will call you later, sir. Thank you, sir.
Thank you. Thank you.
Now, I would call upon Ms. Helen Kirpa to introduce our resource person, Dr. S. Dhanashekhar, sir. Good morning to one and all present here. I am Ms. Helen Kirba from 3rd BSc Mathematics with Computer Application. It is my great honor to introduce our guest, Dr. S. Dhanashekhar, who is an assistant professor in the School of Advanced Sciences, Vellore Institute of Technology. He holds a PhD in Mathematics from Bharathiar University. He also worked as an assistant professor in SRM Institute of Technology and in DRBCC Hindu College, and also worked as a lecturer in Sri Ram College of Arts and Science. He has contributed in various research publications and attended international conferences. His academic responsibilities are Math Lab Coordinator and Associate Chief Superintendent in Vellore Institute of Technology. He has experience in part-time teaching in which he has handled MBA and MCA in Velamal College of Management and Computer Studies in Surapet, and also handled BSc Mathematics in Indira Gandhi Jaiti Women's Arts College in Vellore. We are honored to have him with us in our national seminar and looking forward to gain knowledge. Please join me in giving a warm welcome to Dr. S. Dhanashekhar. We welcome you, sir.
கேமரா ஆட் பண்ணேன் சார். சாரி, நான் இப்போ யூஸ் பண்ணுறேன். சார் ஹைப்ரிட். ஆமாம் சார், யூடியூப் ஆன்லைன்லேயும் இருக்கும். ஆமாம் சார். கேமரா ஆட் பண்ணுறேன். இந்த கேமரா ஆட் பண்ணி சொல்லுங்கள்.
கொஞ்சம் ஹைட்
சின்ன வச்சுக்கிறேன் இந்த ரெண்டுத்துல ஒரு லேப்டாப் வச்சுக்கணுமா இல்லை என்னது என் பேர் சொல்லிட்டு இருக்கிற ஒரு யூனிட் தான் பண்ண முடியும். தெரியும் தெரியும் பார்க்குறேன் நூறா தைக்க வச்சுருப்பான் பண்ணுங்க ஒன்றும் ப்ராப்ளம் இல்லை. நீங்க அப்போ எனக்கு வந்து ஸ்க்ரீன்ல சரி ஸ்லைட் மட்டும் இந்த ஸ்லைட் அதில் ஷேர் பண்ணிட்டு வாய்ஸ் மட்டும் தான் இல்லை அதுலேயே இருக்கு அப்படியே இதில் தான் லைவ் போகுது. ரெண்டு பேரும் சைமல்டேனியஸ்லி யூஸ் பண்ணுவோம். அவ்வளோதான். இதில் சேஞ்ச் ஆகுது, இதில் சேஞ்ச் பண்ணலாம். ரெண்டுத்துலேயும் சைமல்டேனியஸ்லி யூஸ் பண்ணுறேன். அதில் கூட இது காப்பி பண்ணுறதுல காப்பி வேறு நீங்கள் வேணால் காப்பி பண்ணிட்டு காப்பி இல்லை இது மட்டும் ஆல்ரெடி இல்லை ஓப்பன் இல்லை போகாது. சாரி
Good morning to all. First of all, I'd like to thank management, principal of EDG Vaishnav College for inviting me to give a lecture on this National Science Day celebrations. Then I would like to thank Sangeeta ma'am, HOD, Mathematics, convener of this National Science Day celebrations for giving me this opportunity to talk among you. Dr. S. Dhanashekhar, working as a supervisor in Vellore Institute of Technology, Chennai. Today, actually, I'm going to talk about basics of physiology and its application. Actually, right? It's very late, no issues for it. Okay. So, today's National Science Day, you all know about it, why it has been celebrated, and we need now this kind of things because the trend of mathematics is going down and all over world, not only in India. Most of the world are facing difficulties. Students are not interested in mathematics because recently we are doing one project in Sultan and Aboma. In that also the mathematics is, students are not willing to take mathematics in their curriculum. That's what we found. We found many things in that. And if you see all the reports of the world report, UN report, and all other things, it says that most of the nations are facing a problem because of COVID. After COVID, right, mathematical skills are going down. That's what they suggest. But now again, right, the invention of the I think last month or we had a great sensation in the world, right? What is that sensation? No, two months back or 1 month back. The world itself, right, changed it. Trump talked about it. What is that? Deep sea. All of you get into the deep sea? Did any ever? You just try it? Deep sea? No. Yes, right. Now, what is the advantage of deep sea than your chat GPT? Logical reasoning. That's what very, very important, right? So, you know who founded that or who made that thing? The very young fellow inside. The very, very young. But now he rules the world. Trump itself talked about it, and Elon Musk actually is actually preparing to acquire another AI, which actually outcomes this because that business goes. Now, what is the advantage of DeepSeek with ChatGPT is you can get anything in DeepSeek. You can get all the codes of any programs. You type it, you will get the codes. That itself a great. ChatGPT you won't get mostly. And also the things which are coming in ChatGPT sometimes it may not be relevant to you. But this will give you the relevant. It's mainly because of logical reasoning. What is the meaning of logical reasoning? Anybody? What is the meaning of logical reasoning? You all studied discrete mathematics? No. No or yes? Yes. What is logical reasoning? What is logical reasoning? No. Right. The logical reasoning is whether we are going to get a result which are validated or not. We are not going to see the truthness, or we are not going to see the what do you call it? This implies this like that. We need to understand only whether it can be validated or not. That's what you are doing in your discrete mathematics. Truth column you are putting, am I right? True, true, false, false. You all remember that? Most of the people will find easy in that, but that's actually basic of mathematics. Okay, one of the great mathematician and the philosopher, Bertrand Russell, wrote a big book called Principle of Mathematics. In that, he done many logical conjecture, meaning of the conjectures. Right. Now, logical reasoning is very, very important because we need to validate our algorithms, whatever thing you are going to say. It may not be connected. For example, I can write a statement, pigs can fly. And then I can write 5 plus 5 equal to 10. I can connect the both by using a word called and or. But I'm not going to bother about whether, right, the pigs can fly and 5 plus 5, 10 or both are related or not. But I'm going to, right, check it up. What is that validity of the given state? That's what the main thing is. Now, when you're talking about logic, we talk about only two things. One is called true, another one is called false. That is 1 or 0. But in our real life, right, nothing is 1 or 0. Am I right? Okay, influence it may be. Someone may be a good person throughout that film. Someone may be a bad person throughout that film. Right? And someone love one girl, right, with 100% love. And that kind of thing only we can see it in the film. Right? That is one. Logical part, we are not going to see the things which are only zeros, which are not ones. We are going to see many things. That means in between zeros and ones, I have many kind of things. For example, right, if I say that any one, right, for example, if I say that some you won't like. So that fellow likes Virat Kohli, right? That means others are disliking him. No, you are not disliking him. Am I right? That means there exists some intermediate points on it. Am I right? For example, also that fellow likes Virat Kohli only for some percentage. If he fails for another December, sir. When will you write your arrears? Alright, to the people. Yes, but you are using the same word. Okay, right? Most of the things hereafter we are going to use AI. Wherever you are using AI, automatically fuzzy will come behind. What is the meaning of AI? Artificial intelligence, right? Why we need artificial intelligence? What artificial intelligence does? Makes reduces the manpower, right? But just a small thing you have to change it, reducing the man's thinking power, right? Please remember that in one, that is 100 years before, right? Human thought that no, we can't able to work more. Therefore, we need machines. So they went on to find out the machines. All the machines now need God. Right? இப்போ ரீசெண்டாக கூட நிறைய டைம் பாத்திரம் தேய்க்கிறது கூட மிஷின் ஒன்று இருக்குதுன்றாங்க. இட்ஸ் அபவுட் 55,000. என்னோட பையன் பார்த்தான் அவன் அம்மா ஹெல்ப் பண்ணுறதுக்காக. ஆனால் அதுக்குள்ளே நீங்கள் போடுறதுக்குள்ளே நீங்கள் பாத்திரமே விலைக்கு எடுத்துருவாங்க. அந்த அளவுக்கு அதில் டீட்டெயில்டாக இட்ஸ் வெரி டீட்டெயில். Nowadays most of the hotels they are using. I saw some of them, right? இப்போ எல்லாத்தையுமே இட்ஸ் லைக் என்எஸ்கே ஒரு பாட்டில் சொன்ன மாதிரி ரைட்டா it's coming up. There are all machines. Those machines we use only for reducing our work power, right? But now we are so lazy that we don't want to think. That's why we are going behind here. One thing. Second thing is AI gives you more thinking power than human minds. But it should be controlled. That's a very, very important thing. For example, I will tell you an example, right? Most of the time in hospitals nowadays, robotics are doing small surgeries, right? In Cropet, one hospital is there, Raila Hospital. It's very famous for liver transplant. In that liver transplant, most of the, that is, they will take some part of the liver of the donor and put it in the person who needs that. They will cut off some part. Now that from the donor, only robotics is going to take. Got it? They are the only one doing that. Only for putting it inside the patient, that the needed patient only done by doctors. Now, robot doesn't know that, right? Whatever it is on the table, it's a human being. Am I right? You just go and see that videos, it is already in the YouTube. How they are doing it is, But robot first they will check it up whether it can peel the right tomato's skin. So that much of accuracy it needs. Okay. So how it is very difficult to do. So that kind of thing AI helps us. So whenever AI comes, automatically this fuzzy logic will come into play. Why it is fuzzy logic is come into play is, right, when something there, it has more number of ways to react. We have most of the time we have a confusion, am I right? When I go out of this college, right, I have to go to Tambram, if I say that, then I have more confusion whether I have to go to Nungapakam, get the train, go there, or if I go to Coimbatore and get something, or if I go to Madurai. So my mind itself having some kind of more number of paths. So I have to decide from that. So now that kind of things can be done by using fuzzy logic. It's not thing. Now you can talk about probability. Why probability is not coming into play? Probability is when it is comes to play is when the thing is certain, that is that thing is already happened, you are going to check it out whether the chances are there or not. Got it? So fuzzy logic is nowadays very important. I don't think so whether we will have a subject on fuzzy logic. I think it will be introduced in only PGs, right? Now getting into the things PPTs, right? So this is, I already told that. First of all, they done 3-valued logic, and then they went on to find out many-valued logic. What is the meaning of 3-valued logic and many-valued logic? For example, if I go to 3-valued logic, when it actually happens? I hope you know, right? Ainsberg principle of uncertainty. Have you come across that? Ainsberg principle of uncertainty. One of the basic of physics. Physics sort of base. That is, it actually changes the. What it says, that is, when it is in quantum mechanics, it's very difficult to find out 2 parameters of a single particle. If you are checking up whether the velocity of the particle, you cannot find out where the particle is. Because when you are checking it up, already it will be in some other place. That's what Ainsberg principle says. Okay. So when that comes, automatically they change it into 3-valued logic. What is 3-valued logic? One is true, another one is false, another one is that is intermediate point. Okay. In that they come upon it. Then they went on to do the many-valued logic. Then it comes as fuzzy logic. Fuzzy logic was introduced by Lofty-Zadeh in 1965. Then now it's changing everything, all the engineering aspects. Okay, most of the products nowadays, right, inbuilt as fuzzy controllers. What is meant by fuzzy controllers? It will control the thing. For example, if I want to control the AC, hereafter some time onwards, please remember that after 5 or 10 years, right, we will always use electrical vehicle. That will be the next revolution in automobile. After 5 years, again you will go for unmanned vehicles. Okay, 10 to 15 years you will see that in this road it's an unmanned vehicle. Now all these unmanned vehicles, we need logical controller. That's called fuzzy logic controller. Right? Now you can check it out. If you type it in the word file, right, any file, if I type first word A, B, something like that, it will actually match just some word to you. Am I right? Nowadays WhatsApp you are having. Am I right? Meta AI. Is that right? Meta AI. Already we know we are lagging of spellings. Now again it actually tells you not to learn spellings. Only you have to just take a code, right? Sir means yes I am. That's all, yes I am. Right? Now that actually how it will do, it actually matches with the thing and then combine it. That's called large language models. Okay? Right? Now okay. Now what is the meaning of uncertainty? Uncertain இது எப்போ முடியும்? Uncertainty. Do you know about Brownian motions? You know about Brownian motions? No. புரியல. What is Brownian motion? Which one? Brownian motion. Brownian motion is nothing but it's a random motion. You cannot predict molecules, right? Where it will go or where it will join. That's called Brownian motion. Why Brownian motion is important? Your financial. The stock market is Brownian motion. We cannot predict it. Have you understood? We cannot predict the things like gold price. We cannot predict it. Am I right? Okay. So that kind of things are Brownian motions. You got it? Right? Now, in this thing, uncertainty comes around anything. For example, you may not have a correct information about a thing. Right? For example, when you want to understand somebody, 50 is 1. That means 50 is old. Right. 51 is 1. 52 is 1. Because after 50, everybody is old. Before 50, that is up to 48, they may be considered as old. Am I right? For example, if one person is having a salary of 1 lakh, and if I have a set, it says that no, whoever got 1 lakh, they are rich. That's what I'm telling you. If one person is getting about 99,000, okay, 99,000, is actually less of only 1,000. But he may not come into the classical set as a rich person. Alright? He will be called poor. But that is not fair, no. Right? That's what. Okay? Like in cricket also, right? If somebody is legend, whoever has little power with that fellow won't be considered as a legend. That is what happened to Rahul Dravid. Am I right? That is what happened to Sourav Ganguly. Because that time Tendulkar was there, therefore he is considered as a legend. But these fellows are not on par with that fellow, but they are little bit lesser, but they are not called as legends. You got it? That's not a fair thing. Okay? That's why this fuzzy logic comes into this, right? So when they used this, they used it at right. This is called Sendai subway. Actually, it's called automatic train operation. In Japan, actually, they use this. Automatic train can be controlled by automatic system. Nowadays, in Chennai also it will come at some point of time. They add that. They don't have any kind of people to drive or people to do that. When it comes and stand in the station, automatically door will open. After 2 or 3 minutes, automatically it will close. Then it will start. It won't be there for that. It is automatically controlled. Okay? Right? Now, these are all the things they can use it. So this is the advantages of fuzzy logic. Okay? Right. Now, these are all not needed. Fortunately, you all escaped, right? Now, at last we will solve only one example so that you will understand the power of this fuzzy logic, right? Now, this example is from image processing. Okay. So, do you know what is image processing is? Am I right? What is image processing? Do you all, anybody knows that? What is image processing? No. See, the two things which I done a mistake, you are also doing the same mistake, please don't do it. Because my settlement got late because of that, right? When we are here, right, don't think that, right? Study well, it's a very important thing. First thing, take it in a very serious manner. It's a very important thing. Okay? So, because I am the best example for it, right? Okay. This is what the thing is under it is the image. Now this is what the thing is image. Image model comes.
image sensor cancer patients.
Yes. And the other is this one. Now if you see this, actually my research scholars came, Ravinder and Raghavendra and another girl is there, right? They are doing in this image processing. Now if you see this, right, image processing, that's the original image, that is the first one. That original image has been enhanced and it is giving us a thing here. See that how much difference you are making it by using the image processing tool. Now where it is very useful, if you see all the things, for example if you see this last one, got it, this one, right? Now when I enhance this, I can understand that there is a statue about something. Somebody is standing like this. Right? This is totally happened because of the mathematics. Not anything. Basic behind is fuzzy logic, intuitionistic fuzzy, and then matrices, linear algebra. The whole image processing is about linear algebra. All of you are studying linear algebra? Yes? How many of you are feeling easy when you are taking matrices? We always think that matrices are easy. Am I right? No? Huh? Yes. Yes or no? Because I was also like that. That's why I'm asking, right? But matrices are very, very important in all the aspects. That's why they actually taught us first matrices. Because anything can be converted into matrices, then you have plenty of resources out there for matrices. For example, I can make features of each and every product as a matrix. So that I can do many things, so that I can reduce the features of that. By features. For example, when I take my face as a photograph, right, there exists a normal features will be always there, but there exists some kind of abnormal features will be there. Right, I'm right. Because if I know the abnormal features, because normal features I already know, because I have a construction thing is there. Only I have to remember only the abnormal features. Am I right? How we are remembering a particular person? How we are remembering? Everybody is having same two eyes, right? One nose and one mouth and two ears. Everybody is having the same. But what is the thing we are seeing, that the abnormality is actually captured in our mind and it is stored. Am I right? It's not so that all the other things. Are we concerning about when somebody we are seeing that? We are checking it out whether that fellow is having two eyes, whether that fellow is having one nose. We are not checking. Are we checking? No. It is because it is automatically there. In your mind it is automatically imparted. What is the main thing? We will understand the different features of each and everybody and we remember them. Am I right? That's what called features extraction. You got it? So that you can easily, feature reduction can be done by using matrices. Okay, you are taking a photograph in your mobile and you are rotating it. Am I right or no? It's purely about mathematics. It's only about matrix multiplication. Nothing is doing this. That will take your image as a matrices, pixel as each and everything. For example, if you take it that picture picture can be converted into matrices. If you go to the MATLAB and do IM read some image, if you give, automatically it will read as a matrices. It will read as a matrices. Then you are rotating it. What is the meaning of rotation? You are taking the rotational matrix and multiplying that matrix. That's all. Right? When you are, what do you call, making the inverse of it. Okay? That's purely because of matrix. You got it? So, in this one, what we are doing is that one, we are taking the picture first. Go to the algorithm. Flowchart. Flowchart. Now what we are doing is, we are taking a low contrast image, one thing, and we are going to take each and every pixel, find out its membership function. That means how it belongs to that thing. Then we will find out its complement. Right? Then we will find out the hesitancy. Then what we will do is, we don't want complement. What is the complement? Which is not that picture. We are actually, what do you call, omitting that. We are taking only the membership with hesitancy, combining it, we are getting the enhancement. Right? That is, we are taking whatever it belongs, we are taking converting this, from this we are finding out whatever not belongs. After that, we are finding out the hesitancy by using this 2, then adding this membership and hesitancy, I will get more enhanced image. You got it? Where this is useful? This is useful in mammography. Okay, all the cancer, right? Whatever the MRI scans they are taking, no? It is useful there because you cannot go on put the artificial lights inside our body. Am I right? We cannot send artificial light to check it out whether, right, I have a brain or not. It's actually capturing a natural, whatever it is inside. So I have to enhance that. So there, it has a very vital role. Now, this is how the fuzzy logic is all about, right? In your medical term also, if I want to check it out whether that fellow wants a transplantation or not, then I have to make some recommender system and I can do it. Right? Please remember that you are all max students. Don't think that now, right? You cannot do anything. Because when they actually put it in BSc Max, they told that at least tuition and thousand படிச்சுக்கோ அப்படின்னா என்ன சேர்த்து விட்டாங்க புரியுதா என்னோட அம்மாவோட அண்ணா அதான் சொன்னாரு பிசிக்ஸ்லாம் படிக்கணும் தம்பி அது படிச்சுன்னா டியூஷன் கூட எடுக்க முடியாது மேக்ஸ் சேர்ந்து படிக்கணும் பட் நவ் இட் இஸ் நாட் லைக் தட் ப்ளீஸ் ரிமெம்பர் தட் இப்போ நான் சொல்றது உங்களுக்கு சிரிப்பா இருக்கும் ரைட்டா பிகாஸ் ஐ எம் ஒர்க்கிங் இன் பிஐடி சென்னை those people are seeing the contemporary, right, corporate, how the contemporary corporate is needing us as a mathematics. Please remember that. Purida, all the core companies, நீங்க பார்க்குற ஓகேவா கூகுள்லேருந்து அமேசான்லேருந்து எல்லாருமே இன்டர்வியூக்கு வராங்க. Everybody needs mathematics. Please remember that. Don't think that அதை சேர்ந்துட்டு நீங்கள் வேஸ்ட் பண்ண நினைக்காதீங்க. If you finish this and go to data analysis or AI and ML, because all the mathematics people are eligible to do that. AI and ML, artificial intelligence and machine learning for data analysis, then you can get good salary in your. Or if you are interested in research, you go to the research. இன்னைக்கு வந்து ரிசர்ச்சுக்கு வந்து they are giving more money. சும்மா போயிட்டு உனெல்லாம் பிஎஸ்சி மேக்ஸ் பண்ணோன்னு பிஎட் பண்ணுன்றவாங்க ரைட்டா நான் பண்ணல எனக்கு வந்து திபரத்து போய் நான் பண்ணேன்னு வச்சுக்கோ பிஎட் பண்ணிட்டுருவாங்க அப்புறம் டீச்சர் ஏதாவது போன்னு சொல்லுவாங்க வேறு எதுவும் சொல்லுங்க டுடே we have more avenues as a mathematicians than computer science students but you are all studying both so you are all studying both that means it gives you more advantage. Don't settle for small things, right? Because world is needing you. Because anywhere mathematics தெரியாதவங்க நிறைய பேர் இல்லைங்க தெரிஞ்சவங்க எவனுமே இல்லைங்க இன்ஜினியருக்கு பாதி பேர் மேக்ஸ் தெரியும் புரியுதா நமக்கே பாதி தெரியும் எனக்கே பார்த்து தெரியாது நமக்கே பார்த்து தெரியும் அப்போ அவனை நம்ம எப்படி எதிர்பார்க்கணும் பிஎஸ்சி மேக்ஸ் படிக்கணும் ரைட்டுங்களா ஓகே ஸோ ஹோப் ஐ கேன் ஸ்டாப் யூ ரைட் பட் ஐ ஹாவ் So I can understand that this class is for finishing your right. If you have any queries, you can ask. No issues. Legal questions you can ask. That is very important. You want to understand any questions, ma'am? No. Any questions? No, not only in fuzzy logic. You can ask. Legal means right academically. Anybody right?
Sir, I have one doubt, sir.
Yes sir.
Sir, if I have some data set, it contains some data collected from some other fields. Okay, is there any restriction in the number of data to be collected
No,
for
not
using logical, that is fuzzy logic?
No, no.
If I have only 10 respondents,
That is minimum is there.
Yes.
Maximum you do.
Yes.
Minimum you should have at least about 250 or 300.
Okay.
You cannot have it in 10.
Okay.
10 won't give you the correct result.
Yes. If some medical data has only 10 to 50,
Then that means you have to adjust your data according to it. Then you have to.
Okay, sir.
For that, I think time series, fuzzy time series.
Yes. Oh, yes.
Fuzzy
Sir,
time
if
series.
some data contains, I could not get all the information from that particular patient from the hospital.
Okay.
So there is some, what is that?
Missing data is
Missing data is available.
That you can clean it. That's not a problem.
That is not a problem. Thank you so much, sir.
So any other queries? Camera on. Yes. No queries. How many of you are going for live study? One. That's all. Who are? Okay. Others? One. not necessarily max. Please remember that. I told you no, now you have many avenues. You can go to data science, data analytics, right? Data analytics is there. I think it is in Great Lake. They are tie-up with the National University of Singapore. I think they are pioneer in Chennai now. But you can go to data science. Most of the universities are in data science. Visara University, VIT University, Shastra. Most of the universities they have data science. Okay. And you can go to AI and ML, artificial intelligence and machine learning. That also you can do. Okay. Not necessarily. If you are interested, you can come. No issues. Any other queries? No. Right. Thank you very much.
Thank you, sir, for your efficient information about the importance of physiology and its application. Hope our student are in great session. Once again, thank you, sir. Now the time is 7:27. Shortly, you are going to reach this room at 11:30. You should be within the room sharp after 10 minutes. 11:40 you should be here. Okay? Now you can
you have your mobile phone with you, Android mobile, right? Android or iOS, anything. In that mobile, I want to show some app, GeoGebra. Already you may know about it. Anybody knows?
I now welcome Dr. P. Vijayalakshmi, Assistant Professor, Department of Mathematics with Computer Application. Ma'am, to felicitate our resource person, Dr. T. N. Kavita.
Hello. Sir,
Now I would like to welcome Dr. J. Kavita, ma'am, Assistant Professor, Department of Mathematics with Computer Application, to felicitate our guest, Dr. L. Palraj Jayasimhan.
ಸರಿ ಸರ್ ಪಾಠ
Thank you, teacher.
Pratham.
Hey guys, after a short break, you're very distracted. Just kindly maintain silence. Hey everyone, please welcome Ms. Shanmuga Priya to give an introduction to our speaker resource person, Dr. T.N. Kavita.
A warm afternoon to one and all present here. I am B. Shanmuga from the Department of Mathematics and Computer Application. So it is my absolute pleasure to welcome Dr. T.N. Kavita for gathering today. Dr. Kavita is a distinguished mathematician and indeed assistant professor of mathematics at SCSVMV University. With a strong academic foundation, she holds a PhD in mathematics, especially in algebra, from the same university that she is working right now. She has contributed significantly to the field of algebra with the numerous research publications, conferences, and presentations, and even editorial roles in prestigious journals. She has also been an influential mentor, having guided multiple MSc and MPhil students. Best Teacher Award and multiple certification of appreciation. Beyond her academic contribution, she and workshops. We are truly honored to have her with us today and we look forward to gaining insights from her vast experience. Please join me in giving a warm welcome to Dr. Kavita.
இதுக்கு இந்த ஜி ஸ்லைடு பண்ணுறது
லேப்டாப்
சொல்கிறீங்களா?
லேப்டாப்
எடுத்துக்கலாம் இல்லையா? ஓகே.
Yes.
I'm Dr. Kavita from Shankara University, Kanchipuram. First of all, I want to thank the management, principal, and our beloved HOD ma'am, Sangeeta ma'am, Kavita ma'am, and the organizers, and the organizing members, and department faculties, and all the lovable students. Thank you for me to be here today. Thank you all for the invitation. Thank you. Before starting, I have a question from you. It's a logical question because previously sir given you some fuzzy logics, right? Logics when it is true, when it is false. In the middle also somewhat something is there that is called fuzzy, right? Is it? It is true, it is 1. If it is not true, it is 0. In between 0 and 1, some of the things are falsified, that is called a fuzzy logic. Is it? Okay, a logical question. Maybe an English question. Can you guess or not? I want to search you. Are you ready? Yes, a puzzle. He is sitting between two mats with ICS. Who is he? He is sitting between two mats with ICS. Yes, good. Very good. Very good. Very good. Very good. Mathematics. He is sitting between two mats. Mat, he, mat with ICS. So mathematics. It's a logic. Harini Deepa. Helen Kirupa. Helen Kirupa. Good. Very good. Answer within a second. Good. Very good. I have some more questions. I will come back. Okay. So now, today my topic is 2D and 3D visuals of recent trends in mathematics. So, just my all the slides are visual presentation only. Only picture. படம் காட்ட போறேன் அவ்வளவுதான். ஓகேவா? ரெடியா? ஓகே. ஓகே. படம் காட்டுறோம்னே ஒரே ஃப்ரெஷ் ஆயிட்டீங்க இல்லையா? So, mathematics only we are studying with a pen and a pencil, that's boring, right? So we visually see something means it's interesting to us, right? So that the 2D and the 3D presentation is very important for us, right? Okay. In that visual, I want to give you some of the in a world without mathematics. Can you imagine any of the few things as one thing? Is it possible without mathematics? A world without mathematics is possible? Possible? No. Yes, it's not possible. A world without mathematics is not possible. So each and every step, each and every move, each and every talk, each and everything are mathematics. When we are wake up in the morning, what's our first action? We are brushing our teeth. So some quantity of toothpaste. Some quantity of toothpaste. Otherwise, we miss every toothpaste from that tube. And the tube like a month paste here, வெளிய கொண்டு வந்து. Clear? Some quantity. So quantity. Here itself, we appear with the mathematics. So maths is present. Realize they are using mathematical reasoning. நம்ம realize பண்றதே இல்ல நம்ம mathematical reasoning யூஸ் பண்றோம். Right? So when the measurement every move, everything is mathematics. அது தெரியாமே நம்ம யூஸ் So each and every move is mathematics. It's a mathematics. Right? It shows that this graph shows every move is mathematics, right? Says next, each and every view are mathematics. Tangent line. When you are crossing a road, it's an asymptote. Without clash with some other vehicle. Just to open it, like this screen will open to you. Here in this, graphing calculator, geometry, 3D calculator, CAS, probability, this every screen is visible. This screen is visible or not? Just you open the GeoGebra means you will get the screen. Is it? Are you got it? Are you got it? equation. What's that equation? Parabola equation. Y equal to x. Okay? You got it? You got it? If suppose you want extend to the 3D view, you just go into the extended view, 3D view. You just click the extended to 3D. You can view it as a 3D view. It's a 3D view. You can rotate anywhere, any axis you can rotate it. Okay? Got it now? So here in the GeoGebra app, first I am telling about that graphing calculator. Just go back and use the 3D calculator. Next 3D calculator. In that 3D calculator, in the 2D over. Next 3D expansion left. Just we have to form a paraboloid. 3D view the paraboloid we can form. Yes. Z equal to x square plus y square. Z equal to x square plus y square. Okay, got it now? Z equal to x square plus y square. X square plus y square. 3D view. You just turn and keep it means it can rotate. It can rotate. You just touch and rotate it means it can rotate. 3D view. Got it or not? You got it. Z equal to x square plus y square. Yes. It rotates. Suppose you want in the ding z equal to x square plus y square. Yes, the same image you can get it, I think so, right? You can rotate and see this image. This is a 3D image of z equal to x square plus y square. Okay, are you interested? So this like this you can do. Suppose you want a plane intersect this image, you just again add a plane x is equal to y, x equal to y. He can cut the cross section of the plane x equal to y. The cross section of the plane. Okay? You can rotate and see the image. It intersects the previous image. Paraboloid. The plane intersects the paraboloid. Okay? This view you can see in the mobile app. It can rotate automatically. You just click it and Achieve means it can rotate. Is it? Got it now? So okay, it's 2D, 3D view. So and one more thing I want to tell you. This is called a G slide, sir. Actually, I am showing you the G slide. You may know about the PPT presentation, right? PPTs you can prepare like this. The G slide you can prepare the PPT. Now it's easy for you to attach the GIF, GIFs you can attach, videos you can attach, pictures you can attach. Automatically it can get it, and all mathematical symbols in that. So many options are there in the G slide. Okay. So you can use the G slide. Just you go to the Google slide. Like this, the image you will get it. You want a blank presentation, you go to the plus and get a blank presentation. And here you have a insert. Insert in that insert image you can insert. Text box you can get it. Shapes you can insert. Diagrams you can draw. And tables you can draw. Automatically you can get it all the tables you want to insert, you can insert the tables. Charts you can insert, bar graph, picture graph, anything. Any charts you can insert, line, word art, videos you can insert, audios only you want audios you can insert with that. So many options are there in the G slide. Okay, ma? So hereafter you can want to present some presentation, you go with this G slide. But only thing you always have to go with the internet. You want an internet connection for that. That's it. You know? So okay, this is called a G slide. It's a useful thing. You please try to use of it. Okay? I think I may introduce the G slide and the GeoGebra app for the 2D, 3D views, and two more things you can learn, right? So, okay, one more question I have, logical question. Are you ready to answer? Ready? Yeah? Okay, a puzzle. It's a logical question only, not mathematical. Okay, are you ready for answer? Okay. A doctor is in Bombay. Are you listen? Are you listen me? Are you with me? Hello? Are you with me? Okay, please listen. A doctor is in Bombay. Doctor's only brother is an engineer. Okay? Engineer brother is in Chennai. But the engineer brother has no brothers. Then who is the doctor to the engineer? Can I repeat again? Yes. A doctor is in Bombay. Doctor's only brother is an engineer. The engineer brother is in Chennai. But the engineer brother has no brothers. Then who is the doctor to the engineer? Then who is the doctor to the engineer? A doctor is in Bombay. Again I repeat. Doctor's only brother is an engineer. Only brother, underline this. Only brother is an engineer. Engineer is in Chennai. But the engineer brother has no brothers. Then who is the doctor to the engineer? He himself. No, he is doctor's brother only engineer. But engineer brother has no brothers. Then who is the doctor to the engineer?
Sister.
Correct. Correct. Sister. Any doctor. Doctor means you only imagine the male doctor. But she is a female doctor. Okay, now we go for our slide. In engineering la vibration analysis and in AI la neural everybody. We can try in the Desmos. Is it equal to sin x cos y? Is it sin x star cos y? I think it shows error. It's a 3D view, so not shows here in the Desmos. So 3D graphing calculator I want. Okay. Mathematical concepts in 2D and 3D we can view here. So this is that image you will get it. Is that equal to sin x cos y? This is the image you will get it, right? So this is the benefit of that G slide I told. Videos we can include, GIFs, videos. So those everything we can include in that slide. So this is your 3D view of z equal to sin x cos y, right? So okay, next. Yes, now I want to introduce the 4 important application fields. STEM. What is STEM, sir? Anybody knows what is STEM? STEM? Science, technology, engineering, mathematics. That is STEM. So in that 4 fields, I want to give some recent trends to you. Okay? Actually, it's not a difficult trend. S means science, T means technology, and E means engineering, and M means mathematics. Okay? So the 4 fields. So all the 4 can include in a single item. What is that? Called pencil. So in that pencil, are you look at that pencil? So in that pencil, rubber will remove graphite. That is science. Rubber will remove graphite. That is science. Okay. So technology. What is the technology included in that pencil? They create a writing device without use of ink. That is technology. Without use of ink, we can use pencil. That is technology. Okay. Next, what is engineering in that? The device inside graphite and backside eraser in that exterior. So the length, diameter, and shape of the device is mathematics. Okay. So all that 4, the STEM field can include in that single pencil. Okay. Yes. STEM analysis. If suppose we can take a x-axis as a science and the y-axis as engineering and mathematics. So the spiral, it makes a spiral. All the 4 can include as a spiral. This is a 3D spiral. STEM analysis. Okay. So mathematical activity like research applications, education, exposition has changed a lot. arithmetic progression, geometric progression. That simple thing only I want to choose to model it as a mathematical form. Okay? Here a number of bacteria in a certain culture. Okay? That doubles every hour. Bacteria doubles every hour. Over hour ko double idea both bacteria. Okay ba? Doubles every hour. If there were 30 bacteria present in the culture originally. So 30 bacteria irukku. A3, what is A3? In the third hour, AR power 2. So, in the third hour, the number of bacteria is 120. In the fifth hour, they are asking second hour and the fourth hour, right? In the fifth hour, fourth hour, A5, AR power 4 equal to 30 into 2 power 4 equal to 480. So, like that, the nth hour, AN plus 1 equal to AR power n. 30, 2 power n. So, likewise, we can model it as a mathematical. Yes, sir? Okay. So no problem. Okay, well, I have a question for you now. Again, take some few minutes. So in the between gap, we will do some problems. Okay. So logical questions are mathematical questions. Okay, some mathematical questions. I have some fruits. Okay, ma? I have some fruits in a basket. Basket full of fruits. Okay. In that basket, I have some count of fruits. That count you may know. How means when I count it by two fruits I should count na one remains. ரெண்டா கவுண்ட் பண்ணேன்னா ஒண்ணு மிச்சம் இருக்கு. ஓகேவா? When I count it 3 threes, again one remains. Okay? மூணா கவுண்ட் பண்ணாலும் ஒண்ணு மிச்சம் இருக்கு. நாலா கவுண்ட் பண்ணாலும் ஒண்ணு மிச்சம் இருக்கு. When I count it by 4s, again one remains. When I count it by 5s, again one remains. When I count by 6, again one remains. When I count it by 7, nothing is remains. Everything over. Okay, ma? By 7, I count it na. Everything over. So how many fruits are there in that basket? 40. By 7, okay. I count by 6 na 1 should be remain na. 46. I count by 5 na 3 remains na. 1 da remain ஆகும். ஆமா. 1 தான் ரிமைண்டர் வரணும். 49 னா 5 ஆல நான் கவுண்ட் பண்ணும்போது 5 ஆ கவுண்ட் பண்ணும்போது 1 தான மிச்சம் வரணும். ஆனா 3 வந்துருமே. எதுக்கு 4 வருது? ரெண்டா எண்ணினாலும் 1 தான் மிச்சம் இருக்கணும். 3 எண்ணாலும் 1 தான் மிச்சம் இருக்கணும். 4 எண்ணாலும் 1 தான் மிச்சம் இருக்கணும். 5 எண்ணாலும் 1 தான் மிச்சம் இருக்கணும். 6 எண்ணினாலும் 1 தான் மிச்சம் இருக்கணும். 7 கவுண்ட் பண்ணும்போது மட்டும் தான் without reminder it cancelled. அந்த நம்பர் என்ன? by 3s, 1 remains. Count by 4, 4, 4, 1 remains. Count by 5, 5, 5, 1 remains. Count by 6, 6, 6, 1 remains. But count by 7, nothing remains. No. நீங்க கொஞ்சம் பெரிய நம்பராவே கெஸ் பண்ணலாம். 3 digit numbers. செவன்ல மட்டும் ரிமைண்டர் வராது. 61 நான் more than 100 சொல்லிட்டேன். இங்க கேப் கிடைக்கும்ல மறுபடியும் ஏதாவது ஸ்ட்ரக் ஆகும்ல அப்ப பாத்துக்கலாம். ஓகே 7a வாங்க. Exactly 7 to 5. Okay. So the bacterial growth two dimensional presentation ல பாக்கும்போது நம்ம actually mathematics வந்து maths ஆ படிக்கிறதை விட view ல பாக்கும்போது easily we can understand, right? So it's a self explanatory. அதுக்காக தான் நம்ம graph படிக்கிறோம். இப்ப statistics ல கூட பாத்தீங்கன்னா statistics ல data collection, next classification. Statistics படிக்கிறீங்களா? Do you have a statistics subject? Yes, good. Data collection, classification, classify பண்ண data tabulation, and then tabulated data should be presented as a graphical representation, right? Is it? So in the graphical representation என்னெல்லாம் graphs use பண்ணீங்க நீங்க? bar graph, pictograph, histograph, okay curve, two dimensional, right? It's a self explanatory. இப்போ நமக்கு டெக்னாலஜினாலே ஃபர்ஸ்ட் நமக்கு கேம் ஒரு கிரிக்கெட்டை வச்சு பார்க்கலாம். ஓகே, ஒரு சிம்பிளா ஒரு லீனியர் ஈக்குவேஷனை நான் ஃபார்ம் பண்ணணும். லீனியர் ஈக்குவேஷன் ஃபார்ம் பண்றதுக்கு ஒரு இன்டர்நேஷனல் கிரிக்கெட் மேட்ச்ல இந்தியாவும் ஸ்ரீலங்காவும் விளையாடுது. அதுல ரெண்டு பேட்ஸ்மேனோட டோட்டல் ஸ்கோர் வந்து 189 ரன்ஸ். இதுல எப்படி லீனியர் ஈக்குவேஷனா ஃபார்ம் பண்றது, அதாவது மேத்தமேட்டிக்கல் மாடல் எப்படி பண்றது, சிம்பிளா மேத்தமேட்டிக்கல் மாடல் எப்படி பண்றது, அதுதான் நான் சொல்லிட்டு இருக்கேன். இதெல்லாம் உங்களுக்கு ரிசர்ச் படிக்கும்போது உங்களுக்கு ரொம்ப யூஸ்ஃபுல்லா இருக்கும். சிம்பிளா ஒரு ஒரு real life situation எப்படி mathematical model ஆக்குவீங்க? How can you made it as a mathematical model in a real life situation? So real life situation ஒரு சின்ன mathematical model முதல்ல நீங்க generate பண்ணும்போது அதுக்கப்புறம் அதை research நீங்க ஈஸியா கொண்டு போயிடலாம். ஓகே? So ஒரு simple situation தான். ரெண்டு பேட்ஸ்மேனோட டோட்டல் ஸ்கோர் 189. இது எப்படி ஒரு லீனியர் ஈக்குவேஷன் ஆகுது? x y ரெண்டு பேட்ஸ்மேனோட ஸ்கோர்ஸ் எடுத்துட்டீங்கன்னா x + y = 189. இதான் மேத்தமேட்டிக்கல் மாடல். ஓகேவா? சரி, இது வந்து ஓல்ட் ஒன். இப்போ இந்த நியூ ட்ரெண்டுக்கு கொண்டு வரலாம். நான் ஜியோஜிப்ரா சொன்னேன்னா உங்களுக்கு ஓகே? அந்த ஜியோ
அனைவருக்கும் வணக்கம். இந்த வீடியோவில் பந்து சென்ற பாதை ஒரு பரவளைய பாதை வடிவில் இருக்கும்.
வரைய முடியும்னு இப்பதான் உங்களுக்கு ஜியோஜிப்ரால போட்டு காமிச்சேன் இல்லையா? y = x² ஈஸியா parabola draw பண்ணோம் இல்லையா? Just you can draw a parabola in the GeoGebra and fix that parabola into that arc of using a gravitational force, anything can come down to the earth, that is called a projectile, right? Is it or not? Is it? Yes. So next, because STEM analysis la science, technology முடிஞ்சிச்சு. Next என்ன? Engineering. Engineering நான் சிம்பிளா ஒரு எக்ஸாம்பிள் Pythagoras theorem யூஸ் பண்ணிருக்கேன். Just ரெண்டு பேர் just Anita and Ella start at the same intersection. Anita walks east at 4 miles per hour and while Ella walks south at 3 miles per hour. So they are communicating with a two-way radio that has a range of 2 miles. For 2 miles pass பண்ணதுக்கு அப்புறம் they should communicate each other. Okay? So how long after they start walking will they fall out of radio contact? So எவ்வளவு தூரம் அப்ப அவங்க நடந்திருப்பாங்க அங்கே இருந்து ஸ்டார்டிங் பாயிண்ட்ல இருந்து அப்படின்னா நமக்கு ஈஸியா Pythagoras theorem. What is that? Hypotenuse sine square is equal to opposite sine square plus adjacent sine square. Simple equation. இத mathematical formulate பண்ணிக்கிறோம். Just இத ரிசர்ச்சுக்கு பேசிக். ஒரு real life situation how can you model it as a mathematical form? How can you model it as a mathematical form? This is called a research base. First ஒரு mathematical formulate பண்ணிட்டீங்கன்னா and then you go to next level. Okay? Yes. So here the time is 0.4. Okay? Yes, Pythagoras theorem using the GeoGebra.
4 நோட்டீசஸ் கேட்கும் ஓகே கொடுத்துக்கலாம். அதே மாதிரி B and A 4 vertices கேக்கும் ஓகே கொடுத்துக்கலாம்.
Hypotenuse square, we can adjust it and find easily. That's it. How much distance they covered now, you just adjust the triangle and then you find it easily. You can use the calculations here. Okay? Next.
4 vertices கேக்கும் ஓகே கொடுத்துக்கலாம். அதே மாதிரி B and A கொடுக்கும்போதும் நம்பர் ஆஃப் vertices எவ்வளவுன்னு கேக்கும் 4.
உங்க பேர் என்னன்னா டைரக்டா பேரு சொல்லாம என் பேர் கவிதானா கககா கவி கதா கத அப்படி சொல்லுவோம். தெரியுமா உங்களுக்கு ஒரு எழுத்து ஏதாவது ஒரு லெட்டர்ஸை ஜஸ்ட் இன்க்ளூட் பண்ணிட்டு உங்க நேம் சொல்லணும். இல்ல ஏதாவது ஒரு மெசேஜ் நம்ம கன்வே பண்ணும்போது டைரக்டா கன்வே பண்ணாம ஜஸ்ட் ஒரு ஏதாவது ஒன்று ஆட் பண்ணி கன்வே பண்ணுவோம். ஏதாவது ஒரு லெட்டர் காமன் லெட்டர் ஒன்று ஆட் பண்ணி கன்வே பண்ணுவோம். ஏதாவது விளையாடி இருக்கீங்களா நீங்க? இப்பெல்லாம் விளையாடவே டைம் இருக்கிறது இல்லை, மொபைலோட ஸ்பெண்ட் பண்ணுறதுக்கே டைம் நிறைய பண்ணுது. ஓகே, ஸோ வி ஜஸ்ட் ஸ்பெண்ட் அவர் டைம் வித் மொபைல் ஃபோன் ஆல்வேஸ், ரைட்? ஸோ ஹியர் the cryptography is the same thing. Just we okay, இப்போ nowadays mailல போயிட்டு நீங்க பாஸ்வேர்ட் போடுறீங்க, you just put a password, right? It takes a password. Zero is space. Space I just put it as 0. And A equal to 1, B equal to 2, likewise 26 letters I should take as numbers, right? And later this message converted as R is equivalent to 18 now. Okay? Converted as 18. And E is converted as 5. And D converted as 4. Like that, the message converted as a numbers. And I make it as a matrix. You know already, A into B matrix means AB matrix. Suppose the same A matrix multiplied with B inverse, what you can get it? X equal to AB, okay? X into B inverse na, again you will get it the A matrix, right? Is it or not? Inverse matrix, okay. So the simple mathematical logic we can use here to any of the B matrix you can take it. How to comfort with the multiplication, that's it. Okay, or when you can when you can take a multiplication matrix. What is the yes, good. 2 cross 3 matrix now. How about the next multiplicand matrix? What is the order of the multiplicand matrix? 2 cross 3 means what is the order of the multiplicand matrix? Start with. How many rows should be? 3 rows? 3 columns. Okay, 3 rows should be, right? Okay. Like that, a comfort matrix you can take it as a B matrix. You just multiply AB matrix. It's a encoded message. Now we encoded the message. This is the encoded message. And now the encoded matrix AB matrix can be sent to the sender. Okay. And B inverse matrix also included with that. You just multiply that with B inverse means we will get it the reverse A matrix again. We will get it the A matrix again. called cryptography. In the cryptographic form, the computer science we are using cryptographic system. We are using system in that. Okay, 0-1 messages we can conduct binary system. We are using the binary system in computer science. Here you are using the mathematics to encode and decode. Okay, ma'am? Got it? Okay, fine. Okay, next, finally, engineering over. Next, mathematics. Ordinary differential equation. Are you finding the answer for that? 721. Correct. So many answers are. All of you have a subject now, ODE, ordinary differential equation. Okay. Now a model of ordinary differential equation for a situation. T is time and A is a quantity. Quantity of medicine or number of bacteria, anything you can take it. Okay. We just model it as a mathematical result or output function. Right? We interpret the ordinary differential equation dA equal to f dot dt. dA equal to f dot dt. So here it is a linear form and step function, unit step function. Already you were studied in Laplace equations. Anything you can study the unit step function, right? One step you can move, and the function can time plus the next move of the particle. So A into t plus f dot d. Okay. So this is in the form of 2 dimensions. The curve is like that. Okay. Next move is there. Next dA by dt equal to 0. This means dA equal to 0 into dt. That is 0, right? So next change. No changes in that. Oh. A does not change. Only linear. Okay. A does not change, right? Yes, good. So dA by dt equal to 2. This means dA equal to 2 into dt. 2 times. It changes by 2. It changes by 2. So 2 into dt, right? So by 2, 2, 4, 6, 8. The reduction is large when A is large and getting small when A is getting small, right? So this is a curve. It's a curve, right? So two-dimensional view. Next. Yes, sir. Now many of the computer science students also is there, right? Computer application, right? You may know the Pascal triangle, right? Know the Pascal triangle. For what purpose we are using Pascal triangle? Mathematics students are using Pascal triangle for some purpose, right? So formation, permutation combination. Okay, next. Number system. In number system, in algebraic system. In algebraic system, what we are using Pascal triangle? What is Pascal triangle? 1, 1, 1, and 1. the whole square. A square, reduce A and all the A cancelled, B square, right? So like that we can form all any type of A plus B the power or binomial expansion, any powers, and find using the Pascal triangle coefficients. Just coefficients are there, you just include the variables, right? That's it. So for this purpose we are using the Pascal triangle. Once you are seeing this Pascal triangle for this purpose only, but once you are seeing this in a two-dimensional way, these are the counting numbers, and these are the triangular numbers, and these are the triangle. Once you see in the two-dimensional way, so what is tetrahedral? The triangular number now 1, 3, 6, 10, like that numbers are called triangular number. And square numbers means 1, 4, 1 square, 2 square, 3 square, 4 square, 5 square, like that. That is called square numbers. And the pentagonal numbers now 1, 5, 12, 22, these are pentagonal numbers, and hexagonal numbers 1, 6, 15, 28, these are pentagonal numbers. Okay, these patterns are now included in the it gives the pattern of Sierpinski's triangle. What is that Sierpinski triangle? Sierpinski triangle is a pyramid model triangle. Now only the Shivaratri went, you may go to the temple of Shiva. Shiva temple, so many of them may went there, not? Okay. So in that Shiva temple, you may see some Sahasralinga. You know about that Sahasralinga? ஒரே ஒரு லிங்கம் இருக்கும். அந்த லிங்கத்துல நிறைய குட்டி 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 100 லிங்கம் இருக்கும். குட்டி குட்டியா 100 லிங்கம் இருக்கும். This same model is called. பாத்துக்கிட்டீங்களா? கோயில்ல சின்ன ஒரு லிங்கத்திலேயே ஒரே ஒரு லிங்கத்துக்குள்ள நிறைய குட்டி குட்டி லிங்கம் இருக்கும். ஒரு 100 லிங்கம்ஸ் இருந்தா சஹஸ்ரலிங்கம் சொல்லுவோம். அந்த சிர்பின்ஸ்கியோட அந்த 3 டைமென்ஷனல் மாடல் இது ஜியோஜிப்ரால தான் மேக் பண்ணேன். எனக்கு இங்க வந்து மேக் பண்ணி காமிக்கிற அளவுக்கு டைமிங் இருக்காதுங்கிறதுனால நான் போட்டு சின்னதா ஜிஃப் மாதிரி ரெடி பண்ணி எடுத்துட்டு வந்துட்டேன். ஜிஃப் எப்படி ரெடி பண்ணணும் அப்படின்னு சொல்லிட்டேன். இது ஜியோஜிப்ரால பண்ணது. அதை அப்படியே ஜஸ்ட் சின்னதா அந்த பேண்டிகாம்ங்கிற வீடியோ மேக்கர்ல வீடியோ பண்ணி கொண்டு வந்திருக்கேன். பட் ஜிஃப் எப்படி பண்ணணும்னு டைம் வந்துச்சுன்னா டைம் அவைல்ஸ் எனக்கு அவங்க மேக்கேஜ். ஓகே, எஸ். ஃபோன்ல ஜிப் பண்ணுவீங்க நீங்களே, உங்களுக்கு தெரியும் இல்லையா, ஈஸியா பண்ணுவீங்க. லேப்டாப்ல எப்படி ஜிப் பண்ணணும் டைம் பண்ணுவோம். Total of this 16, total of this 32, 64, 120. Some pattern. Okay, it's amazing. Doubles. Okay, is two doubles na 4 doubles na 8 doubles na 16 16 doubles na 32 Okay, into 2. Okay, it's a good pattern. Yes, next expansion of 11 in that pattern. Five one is there, right? Is it? So how can it means you just simple the digit just overlapping. The digit just overlapping. Keep the 0 there. Keep the 0 there and then keep the 1 with this 5. Right? So the 4 square means 6 plus 10. So likewise, so many patterns are there. 3 square na 3 plus 6. 4 square na 6 plus 10. 5 square 10 plus 15. So it may be a triangular form in that pattern. Maybe a triangular form in that pattern, right? Is it right? Do you understand? Are you with me? Yes. Next is symmetrical pattern. Symmetrical is nothing but a mirror image. When I keep the mirror middle of the portion, it shows the image. So mirror image is called symmetrical pattern, right? So the symmetrical Pascal triangle, but within that, so many patterns are there. It shows. And we can see using a two-dimensional way, so many patterns we can find it from it. Okay. Next one. Head or tail, right? Head or tail, two options. So okay, one head, one tail, one head, one tail. Suppose two coins tossed. HH, HT, TH, TT. Okay. So one, two, three. Okay. Sorry, 1 2 1. HH, HT, TH, TT. Okay, no? So next to three coins. So all the resultant we can get it from so how many 2 hertz? Exactly 2 hertz now. The probability is 6 by 6. How you find using the triangle of the sixth line are 1 2 3 4 fifth line. Fifth line shows you the result. How can you find? Actually 2 power n, right? So 4 kind tosses. 2 power n and 2 power 4. What is 2 power 4? 16. So the total of the fifth row is 16. 1 plus 4 plus 6 plus 4 plus 1. Is it? Okay. So next Fibonacci sequence. No. Yes. Consecutive two numbers. So Fibonacci sequence we can form using the Pascal triangles. Here 1 plus 1, 1 plus 2, next to 1 plus 3 plus 1, 1 plus 4 plus 3, 1 plus 5 plus 6 plus 1, 1 plus 6 plus 10 plus 4. So 1 naturally we got it in that nature. So in the plants, the Fibonacci sequence can form automatically. In that to form the plant. Forms a Fibonacci spiral. Okay, got it now? Yes. Next. Okay, not only in plants. So the Fibonacci can to the golden ratio. When you divide a circle into golden proportion, its dark length gives the golden ratio. Okay, here 137.5 degree angle the golden ratio can form. In the case of pineapple, the pineapple Fibonacci nature. In nature, I told you in plants the Fibonacci is naturally formed. The similar way in the fruits also the Fibonacci can form. It gives you the strength of the strongness of the fruit and beauty or strength of the things. That is. Is it or not? So in that formation only gives that hardness. This formation only gives that hardness. So Fibonacci form, two Fibonacci form is there. Yeah, opposite. Okay. Here in sunflower also. In flowers also. Not only in plants, not only in fruits. In flowers. Fibonacci. Okay. Says Fibonacci spiral. You can look at that closely. So the Fibonacci spiral can be. Can you see that? Are you with me? Yes, in fruits also is there. Here, in bananas, 3 sections and apples in 5 sections. Okay. So here this is a cauliflower. So in vegetables also, not only in plants, flowers and fruits, in vegetables also, the Fibonacci spiral is there. Here, in vegetable, the Fibonacci spiral. So here, I said the Fibonacci spiral is called as a golden spiral, right? So the golden spiral, not only flowers, vegetables and fruits, in flowers also is there. Here in this rose petals, 1, 2, 3, 4, 5, the spiral can form the Fibonacci spiral. I already told you the Fibonacci can use the strongness or just give the table. Not only in plants, fruits and vegetables, in animals also is there. It's a shell. Here golden proportion is there in that spiral. Okay, in starfish also. Here, rectangular pentagon is drawn and the diagonals are added. The five-sided star or pentagram is formed. Okay, so where the sides of the pentagon are 1 unit in the Fibonacci is there not only in plants, fruits and vegetables. In human also the Fibonacci characteristic is there. The golden ratio is there in our hands. 8 fingers in total. Okay. 5 digits on the each hand and 3 bones in each finger. Okay. 2 bones in the thumb finger and 1 thumb in each hand. Okay. So that is the Fibonacci. 1, 2, 3, 5, 8. So the Fibonacci formation is there, right? So now here in we strengthen now. Here there some spiral formation is there. Okay. So this is the golden ratio actually. The ratio, the long side divided by the short side. Long side plus the short side divided by long side. That gives the ratio 1.618. That is pi value. The golden ratio. Okay. So when the golden ratio is there in that thing, it gives the beauty or strengthenizer. Okay. So here the face is a beautiful face. It should be contains the mathematical. Then she is beauty. Then the golden ratio is perfect. She is beautiful. When the ratio is not perfect, she is not beautiful. Okay. So by golden 0, 1, 1, 2, 3, 5. That one you know. This is the Fibonacci sequence. The ratio of each number under the previous number gradually approaching the 1.618 or 5. Gradually, not exactly. Okay. Yes, the golden ratio also known as the golden. Equals approximately 1.618. Approximately 1.618, not exactly. Okay. Usually written as a Greek letter pi. It is strongly associated with the Fibonacci sequence. A series of numbers wherein each number is added to the last one. Okay. So this is the ratio, sir. It should be the perfect one. Here, this is the golden ratio and the golden ratio in nature. Ratio, golden ratio. Okay, here, how can the golden ratio can form? 5 divided by 1 and 1 divided by pi minus 1. The ratio between the previous number and the next number answer. No? So next, pi square minus 5 minus 1. It forms a quadratic equation. This is the ratio. Okay. So the many buildings have golden ratio. This is the ratio 1.6. View of the Egypt pyramid with golden ratio, and this is a building of this is a church of London, St. Paul's Cathedral. It's with the golden ratio. Many of the cars have the golden ratio. Then only it's a very famous So we can find the golden ratio of your face. The golden ratio of face we can find. Nowadays we have more websites. You just upload your photo and find your face is with the golden ratio or not. If it is with the golden ratio, nearer with the golden ratio, you are beautiful, or otherwise you are not beautiful. Suppose you are not beautiful.
Mini auditorium, Govardhan Block.
Wait. Second year students assemble in the class Krishna Talk by 1:45.
Thank you.
சார் அது இங்கே முடிஞ்சிச்சு சார். மினி ஆட்டோரியம் தான் பண்ணணும். அதுக்கு என்ன பண்ணலான்னு? பேனர் வச்சு விட்ருவா சார்? ஓகே சார். இருறா நான் வரேன். ரெண்டு தானே எடுத்தது சார்ஜர்
நான் போயினா அந்த கம்யூனிகேஷன் இருக்கு சார்
போயிட்டாமா
ராமச்சந்திரன் இருந்தாரு எம்பிஏல இருந்தாரு ஆனா அவர் அப்படியே போயிட்டாரு நான் இருந்த வரைக்கும் இருந்தாரு 5 இயர்ஸ் ஆர்ட்ஸ்ல இருந்தாரு போயிட்டாரு ராஜ்குமார் சார் எம்பிஏ நிறைய ஸ்டூடெண்ட் PhD பண்றாரு
இந்த லேப்டாப் ரெண்டுத்தையும் ஸ்டாப் பண்ணக்கூடாது போடக்கூடாது அப்படியே எடுத்துக்கணும் ஓகேவா மினி ஆடிட்டோரியம்
அப்படியா
என்ன செய்ய யார் யார் வருது இது எங்கே கனெக்ட் பண்ணியிருக்காங்க பாருங்க இது வந்து எடுத்துக்கோங்க இது வந்து யூடி மேம் உள்ள கனெக்ட் பண்ணியிருப்பாங்க எது ஒன்றும் செய்யக்கூடாதுப்பா ஓகேவா கையெல்லாம் படாமல் அடியில் பிடிச்சி அழகாக தூக்கிட்டு போங்க இது அரைச்சிடலாம்
மேம் இது ஒன்று லைவ் போயிட்டுருக்கா
ஆமாடா லைவ் போயிட்டு இருக்கு
நடந்து போகிறதெல்லாம் காட்டுவாங்க
இல்லை காட்டாது அந்த இது வச்சாச்சு ஏய் வருதா இல்லை ஒரே நிமிஷம் அந்த சார் வந்துட்டாங்க இல்லை வச்சுட்டான்னு நினைக்கிறேன் அந்த இதுதான் தெரியும்
Sore nanya Cika tahu tapi
Scopus and UGC research journals, and authoring book in his field. His dedication
Once again, I thank you for the topic. Today, I would like to share a few things in the domination theory. Actually, the domination theory is the one of the branch in the graph theory. So, in the first year, maybe I hope some of the students are there. And the UG students, you have studied the graph theory. That is one of the paper, and in MSc also there is advanced graph theory. In that advanced graph theory, there is a topic domination. So actually, I have learned this topic. My topic is mostly research oriented. So we can understand the concepts. Further, it is very useful for your further research. So this domination theory. In the graph theory, there is a book. It was 200 years before. Coney has written the book in 1936. The book name is here it is given. That is the book name. Theory. It is in the language. This book is written by the Coney's. You are very familiar in the Coney's problem in the graph theory. So he has written this first book. So among huge diversity of the concept that appears while studying this graph theory subject, a lot of popularity in one topic. Extensively researched in that topic. That topic is a domination theory. So there are a lot of concepts as introduced in the domination theory. Different types of dominations. There are thousands domination theory concepts is introduced. With that, I'm going to discuss the basic things in the domination theory. So this concept actually arises in the facility location problems. So facility like a hospital, fire station, and a radar station, radio stations. So some facilities we have to place in the correct locations. Then only everyone has used that source. So in that, the domination in graphs helps to deciding and finding the locations where we have to place the hospitals and fire station. Like these are all the facilities are very important So in that way, the domination helps to identify the facilities locations. In the network also, uh, where we have to place the monitoring network. So this and all. Actually, for this concept, the domination theory arises in that field. So then, in the concept domination in graph is introduced first by Glaudberg, okay, in 1950. It is called as a Queen's problem, chessboard queen. Actually, the 8 cross 8 chessboard, the chess players are interested to place the minimum number of queens to cover the entire squares in the chessboard. Okay. So, how many queens can be placed to attack the every squares in the chess, to cover all the squares in the chess? Actually, first they place the 8 queens. Here, likewise, we know that the rules. So, how the queen will move in the chessboard. So, first they place here one queen, and here is the another queen, here another queen, likewise here another queen, here and here. There are 8 queens were placed, and this queens has covered the entire square. So, this queen covered the whole squares. Likewise, this queen covers the whole squares in this way, and also diagonally, vertically, horizontally. Okay. So after that, they want to minimize how many queens we can place. So finally, they found 5 queens can be placed to cover all the squares. So here it is given. This all the queens cover the entire squares on the chessboard. By the rules, it move by diagonally, so it covers. If you check, it covers all the squares. Then another, we can place anywhere, but the condition is it has to cover all the squares. Here also, in this also, they place the minimum number of queens, that is 5. So that covers entire the square, or that attack entire squares on the chessboard. They try, suppose if you place in the diagonal elements, how many queens we get. Okay. That also 5 queens, minimum 5 queens. So the 5 queen enough to attack all the squares. Chessboard. And here they have placed in the sub-diagonal. Okay. Here it is placed in the main diagonal. Here it is placed in the sub-diagonal. So historically, the first domination problem came from the chess. In 1850, several players are interested to place the minimum number of queens. In that situation, they found the concept domination theory. Actually, the queens dominate all the entire squares. So it is a mathematical definitions. What is the domination theory? A set S, subset of V of G of matrices in a graph G in a dominating set if every vertex V in V of G is either element of S or adjacent to a element of S. This is the concept, important thing. That entire matrices in the graph either element of S, that means either in the subset, that if it is a dominating set, so either in dominating set or adjacent to that element of the S. Okay. So that through the example we can see. So this is the one graph. Okay. So what is this is the set of vertices, 1 to 7 vertices. It is in the graph. So the set we can take any subset, but we have to check whether it is a dominate the entire vertices are not. Okay. So here, see, suppose I take the subset of vertices 3, 5, whether it is dominate or not. Okay. So in a simple way, we can understand the set of elements in the graph, okay, the vertices in the graph, either in S or adjacent to the element of S. Okay, 3, it is in the element S. Okay, and 5, it is in the element S. What about other vertices? Okay, so suppose I'll take the vertices 1. That has to be either in the vertex set or that has to be adjacent to the S. But I'll take 1. Whether it is adjacent to the vertices of S. S means here we have taken 3 and 5. So we have to check. 1 is either adjacent to 3 or 5, or that should be in the set S. That's not satisfied. It is a subset of the vertex set, but it is not a dominating set because not satisfy that conditions. Okay, because 1 is not adjacent to the set of vertices in S, or it is not in the set S. Okay, so what is a dominating set? Here we have the set 2, so suppose I take the 2. So check the other vertices. Okay, this satisfies. 2 and 5 are in the set S. What about the other vertices? Other vertices should be the adjacent to 2, 5. Okay, so 1 I'll take. It is adjacent to 2. Then I'll take 5. Then 3. 3 is adjacent to 2. Okay. Now here you have to see the other vertices. Okay. Other vertices should be adjacent to the set of vertices in S. Then C4. 4 is adjacent to 5 and also adjacent to 2. Then C7. 7 is adjacent to 5 and also 6. 6 is adjacent to 5. Therefore, it satisfies the conditions. Okay. So all the vertices in the graph either adjacent to the vertices in S or in the set S. So it is satisfied. Therefore, it is called as a dominating set. So then there is a domination number. So many things deal with that domination number. So what is the domination number? So the minimal dominating set, a dominating set, S is called a minimal dominating set. If no proper subset of S is a dominating set. Okay. So there is no proper subset in the dominating set. Okay, that is the minimal dominating set. So the domination number is the minimum cardinality of the minimal dominating set. That is the domination number that is denoted as the gamma of G. So now we will check that in the graph what is the minimal dominating set. Okay. Suppose I take this is the harmonic of the minimal dominating set. Because there is no proper dominating set in this. Okay. So therefore, it is the minimal dominating set. Suppose if you see this example 2, 3, 5. Okay. So you can find there is a subset is a dominating set in this. So 2, 3, 5. 3, 5 is also a dominating set. But there is a proper subset is a dominating set. But for the minimal conditions, there is no proper dominating set. Okay, that is the minimal conditions. So now, in the minimal dominating set, which is the set as the minimum cardinality. So the set 2, 5 has the cardinality is 2, size is 2. Therefore, that number is called as the dominating number. So other sets also here dominating set, but the minimum cardinality. Okay, that is the domination number. So we have the different definitions. It is one of the definition. Other way we define the domination theory. With the conditions, also they define the dominations, dominating set. Definitions is under other definitions. But you can easily understand these definitions. The vertices in the graph, either in S or adjacent to the elements. Okay. So that is one of the application problems. So we can easily understand where we can place the facilities. Okay. Here are the red vertices, red colored vertices. If you place here the facilities like a hospital, fire station, other things, so the remaining vertices can directly access these resources. Suppose if I place in the other vertices, suppose the facilities, if I place here, what happens? This vertices cannot access that. Okay. So this has to go this, then only can reach this place. It cannot access that. So in that case, if you place like this, then all the vertices can access the facilities directly. Okay, because the hospital and other things are very important. If you consider all the vertices are some villages. So among these villages where we can place all the facilities. The condition is everyone has to access with the minimum distance. So that is the domination theory. This is the problem that is considered the smart city applications where we place the sensors and traffic interaction to monitor the pollutions, air pollutions. So the next, another type of dominations, total dominations. This is one of the other type of dominations. The SNTS of vertices in a graph G is called a total dominating set. If the vertex V in B is adjacent to an element of S. So what is the difference between dominating set and the total dominating set? So total dominating set either in S or adjacent S or. Okay. So but here every vertex in B is adjacent to the element of S. So that the conditions, the total domination is introduced. Because in the security systems, if the dominating sets are monitored at other places. Suppose in the first graph, if the red color vertices, this vertices monitor this place and this place and this place. So this monitor this place and 5, 4, and 9 monitor 10 and 8. So all the vertices are monitored by the dominating vertices. Okay. In case if this is attacked, so other the vertices who is in the dominating set that doesn't know whether it is monitored the other vertices or not. Suppose if this is the one security point. Okay. So they viewed all the vertices. Okay, all the places. In case this point is attacked, so what happened? The other security points doesn't know whether they monitored that places or not. So for that case, so the total domination concept is introduced. Here there is the adjacency. So this, suppose if this one is attacked, other one easily identifies. Okay, these places are not monitored. Suppose in case if this dominating vertex has attacked, so this easily identified. So in that the way the total domination has introduced. But in the domination, it is not possible. So that is the concept. If every vertex V in B adjacent to the element of Yes. And the first one is a dominating set. So where we have applied these things and water resource management, optimal placement of the water distribution centers to serve rural urban areas. In this situation, the total domination ensures every household has direct access to the water without any dependency or intermediary. So the forest fire prevention, wildlife conservation, replace the sensors, fire monitoring towers, ranger stations. To place these resources, we can apply the total domination concepts. The next another type of domination is a connected domination. Okay, what is a connected domination set? A connected dominating set is a dominating set in which the induced subgraph. Okay, so induced subgraph that denoted as in this bracket it is induced. So the vertices is dominating. That is connected. The induced subgraph is connected. Then it is called as a connected dominating set. Okay. So the first one is a dominating set. What is the definition actually? It is an induced subgraph is a connected. But here, if you take the induced subgraph, it is not connected. Okay. No well induced subgraph. So if you take this, it comes with that, but this is corresponding edges also. You have to take the induced subgraph. Suppose if you take the induced subgraph of this, you will get this one. That is not connected. You get the different components. So that is a dominating set, but it is not connected. The induced subgraph is not connected. There is adjacency. And this is a connected, this is the total dominating set. Okay. This is the connected. Why it is a connected? The induced subgraph. Check the induced subgraphs. So when you take the induced subgraph, it comes like this. You get this by edges and all this vertices. Therefore, it is a connected. But it is not connected. If you take the induced subgraph with this, it is not connected. Therefore, but it is a total dominating set. This is a dominating set. This is a connected dominating set. It is so the next concept, majority domination. So that concept is introduced by Dr. V. Swaminathan and Jocelyn Manora in 2003. A majority domination in a very practical situation, especially in the decision making. So there are two types of agreement of the decisions in the body of this means they will get the opinion from everyone. Each and everyone. The another part is majority decisions. In this case, the cannot satisfy each and everyone. So how we can come to the conclusion? If more than half of the members are satisfied, so we can accept that, we can come to the conclusions. Many practical are, especially in the decision making. So in that way, that situation, this concept has introduced majority domination concept. Introduced what is the definition of majority domination? So the definition. The graph G is a finite graph with the P vertices and Q edges. A subset, S subset of V of G of vertices in the graph G is called a majority dominating set. The condition if at least half of the vertices of B are either in S or adjacent to the vertices of S. Like same. Cover the entire vertices. So if you cover more than half vertices, that is enough. So in that the concept majority domination. That is the cardinality of closed neighborhood of S greater than or equal to, it is the cardinal integer or upper ceiling, that is the cardinality of V of G by, that is cardinality of closed neighborhood of S greater than or equal to upper ceiling of V by 2. That is more than half of the vertices. It should be half or so another definition, strict majority dominations. This is the definition. So we can add plus 1. The cardinality of close neighborhood of S greater than or equal to, it is the lowest ceiling, the greatest integer, cardinality of V of G by 2 plus 1. That is the strict majority dominating set. So in that, V of G is always the, it is the other proposition, the theorem. V of G is always the majority dominating set for any of graph G. Suppose if you consider the entire vertices, definitely it is and then here also we have the majority domination number that is denoted as the gamma m of G. The minimal majority dominating set, minimum cardinal G is the gamma m of G. So S is the subset of V of G is the majority dominating set of minimum cardinal G, then it is called the gamma m of G of Z. So what is the example? What is the majority dominating set in this? So here V5 and V2. How many vertices are there? There are 17 vertices. So how many vertices has to be dominated? That is only 17 by 2. So we can cover the how many vertices? Upper ceiling 17 by 2. Please state it there. 17 by 2. I hope you all are sleeping. 17 by 2. 8, sir. 8. 8.5. 8. But for this majority domination, we'll take the upper ceiling, therefore it is a 9. So that has to cover the 9 vertices. See here V5 and V12. So V5 this covers, it dominate 1, 2, 3, 4 and 5. Okay. Itself also is counted. So 1. So the V5 dominate 5 vertices. And V12 dominates 4 vertices. Totally 9 vertices. So it is a majority. Majority concept is satisfied. So other sets D2, D3, D4, D5, all are there. vertices, star graph, double star graph, fan graph, wheel graph. For all the graphs, the majority domination number is 1. Even the domination number for the fan graph and the star graph, the domination number is 1. One vertices cover or dominate all the remaining vertices in the graph. Therefore, this 1 is enough to dominate all the vertices. So these are all the basic graphs. For all this graph, the majority domination number is 1. Okay, this is the proof. Okay, we don't go for the proof part. So another position for the cycle. If the graph G is a cycle on P vertices, P greater than or equal to 3, then the majority domination number is, let us upper ceiling, P by 6. P is the number of vertices. Okay. So when the total number of vertices by 6, the fixed integer, the upper ceiling, P by 6. So another one, the graph is a path graph. The majority domination number is that also P by 6. Because we have considered the majority. Majority means in the cycle, you don't need to consider all the vertices because the majority has come. Therefore, automatically there is a path. So therefore, there is the same for the path and the cycle. So the next Peterson graph. So that majority domination number for the Peterson graph is 2. Some bounds. Okay. So in the graph theory, the researcher mainly find some bounds. So the first one is, if G be a graph of order P, it is a complement of 1 less than or equal to the majority domination number less than or equal to lower ceiling of P by 2. So that is the one bound. And so another bounds are with the maximum degree. Maximum degree of the graph, delta of G is mentioned. By using the maximum degree, we can find the bounds of the any graph G. Okay. So any graph, all the bounds satisfy the any structure or any graph structures. So another bounds is majority domination graph degree of the graph. If the maximum degree less than P by 2 minus 1. If you check, all the graphs satisfies this condition, this bounds. So next one is without isolated vertices. Isolated vertices means not connected. There is no edge. There is no adjacent edge. So that for that isolated vertices, gamma m of G is less than or equal to upper ceiling P by 4. So isolated vertices itself dominate. Okay. So here for the majority domination, if you take half, more than half, so that the number is the majority domination number. Then sum of the graphs, union of the graph, Cartesian product. So these are the results if two graphs, any graph. Okay. Graph G1 and G2, the domination, majority domination number of G1 plus G2.
Let's say majority domination number of P1 plus in the another result arrived in the bound in the
two graphs, sum of the two graphs. So these are the proofs. Okay. So another thing, if order P1 and P2, if the two graphs is the path, G1 and G2 are the
path graph, then it satisfies
the majority domination number G1 plus G2 equal to
1. Simply 1 is there. Because when you sum this two graphs, automatically it will become a complete graph. Okay. Therefore, the maximum is one vertices
adjacent to all other vertices of the other graph. So that one vertices is enough. The sum of the two graphs to dominate. So the majority domination is enough. Then next, union of two graphs. For the result of union of two graphs, the majority denomination number, union of two graphs, G1 and G2, it is less than or equal to the majority denomination number of G1 and the majority denomination number of G2. So this is the proof for this result. And another, this Cartesian product. Cartesian product of the two graphs. Our order P1 and P2. Then this Cartesian product is greater than or equal to minimum of that majority domination number of G and H, which is the minimum. That is greater than or equal to the Cartesian of the two products. So there is a famous Ising conjunction in the graph theory. Okay. So everyone has touched this concept, Ising conjunction concept. It's added the majority domination also. And there is a Ising conjunction satisfied for the Cartesian product of two graphs. So in the graph G and H, there is a Cartesian product. That majority domination number greater than or equal to product of that two majority domination. So this is the sum of the two graphs. So I'll take P2 and P3. Okay. Path graph with two vertices and path graph with three vertices. If you sum this two graphs. So from the first graph, the vertices adjacent to all the vertices of the second graph. So this one is enough to dominate the majority vertices. Okay. So this is the sum of the two graphs. Then union of two graphs. In the two graphs, G1 and G2. Then union of this two graph. The result is you get less than gamma f of G1 plus gamma of G2. So it is the grid graph. That is the Cartesian product. But here we have the first graph, 5 vertices. Second graph, 6 vertices. How many vertices need to dominate the majority vertices in the graph? So the total number of vertices here, 5. So 5 by 2. By this majority, it is a 3. Okay. So 1 vertices has to dominate the 3 vertices. So here, suppose if you take V1. V1 dominate only itself and another U2, U1 and U2. But it not satisfies. So we need to dominate 3. So U2. Okay, U2 dominate the 3 vertices itself and the other 2 adjacent. Here is 1 enough, here is 1 enough. Okay, totally 2. But when you take the Cartesian product of this two, you get a grid graph. For this grid graph, there are 30 vertices. In the 30 vertices, how many we need to cover? 50. So we need 4 vertices, dominating vertices to cover the 50 vertices. That satisfies the previous results. In this majority domination, I have just touched the few concepts. Just I have introduced what is the domination, what is the majority domination. There are many results arrived in the majority dominations and various type of majority domination as introduced, like connected majority domination, total majority dominations, and power majority domination. There are so many majority dominations introduced to the various authors. So in the application part of the majority domination, it does not require all the power sources to be active. Only a majority is enough. Majority sources enough in the energy grid stability. For example, in India's smart grid, if more than 50% of solar and wind farms function, that enough. So the grid remains stable without requiring all the sources to be on. That I told you previously. Many situations Next, sustainable agriculture, food and security. In the example, in integrated pest management, controlling pests in more than 50% of crop field and prevent outbreaks across an entire region. Okay, the pest control. So you don't need to cover the entire region. Technologies, overall pollution has reduced significantly dropped. We cannot insist all the factory to adopt the what the green technologies. Okay. So if you 50%, more than 50%, if they adopt, so automatically the pollutions will reduce. So in that cases, we can use the majority dominations. So these are the some applications in the sustainability goals. Any questions?
Yes, sir. Good afternoon, one and all present here. Good afternoon, dear students. Good. Dear student, thank you so much. Thank you for the chief brief introduction. Okay. Dear student, thank you so much. First of all, I would like to thank the management of TG Vaishnav College, principal, head of the department of mathematics, conveners, coordinators of this national seminar. And I would like to thank my dear friend, Dr. J. Kavita, for inviting me for this session. Thank you all the dear staff members of Mathematics Department for giving me this opportunity. I am Dr. V. Vijayalakshmi from SR Valimai Engineering College. Actually, I am very glad to stand over here in front of you all because my research started here only. The previous head of the Department of State, Dr. R. Satyanandan sir, was my research supervisor in 2009. So I am very much pleasure to give as my lecture on this topic, who gave me this research opportunity for me to go through in my life, in my career. Thank you, sir. And my research topic today is fuzzy matrices and its applications. We all know that classical set theory. We know the set theory. What is the set theory called? It is a creation of well-defined objects. So, as you know that it is a well-defined object, in a set this, it is a well-defined set. A set of elements called A1, etc. That all the elements should lie in the set. The characteristic function will be defined as mu of x is equal to 1 if that element belongs to x, otherwise it is 0. Because we can't start the fuzzy logic without the brief introduction about the sets and the classical sets. Next, fuzzy sets is there for fuzzy set theory. There are some differences between the ordinary sets and the fuzzy sets. Here we will deal with the membership function only, sir. You know basic introduction about this fuzzy logic topic. The membership function is lies between the values 0 and 1. The membership function associated with the fuzzy set. The function maps every element of inverse of discourse x to inverse 0, 1. So all values in fuzzy numbers should lie between 0 and 1. So there are differences between the ordinary sets and the crisp sets and the fuzzy sets. So crisp sets divide the different values as 0 or 1. If it belongs to the set means it is 1. If it does not belong to the set means it is 0. If you are listening to the lecture means it is 1. If you are talking to the lecture means it is 0. That is the crisp set. But some of you are partially listening, talking as well. Like that, if you do means it's called a fuzzy set. So fuzzy set defines the value between 0 and 1. It includes both 0 and 1. It defines the full membership. Crisp set defines the full membership. Whereas fuzzy set defines for the partial membership. So it can be either 0.5 or 0.7. The decimal value is between 0 and 1. So for example, she is 18 years old. That is a crisp set because 18 years is a perfect value. It is a crisp set. Above 18 years, it may be 18 and a half or 17 and a half. Above 18 years, it's very different for the normal English language. It has a different meaning. It is above 18 years old means it can be different in months also. That is coming under fuzzy sets. So this is a design for the design and the fuzzy set is for the fuzzy controller. So this is a basic definition of fuzzy set which I give it now. For example, if you take an example, so G1 to G5 be the reference of the students. So I am going to explain about the smart students, like the right students. So here, for every member of every student, I will mark one membership function. That is point. First student G1 may be a smartness up to 0.4. G2 is 0.5. G3 is 1, and G4 is 0.9. So this how the value indicates depending upon the smartness of the students. I am indicating the membership value. Do you all follow what I am giving? So there is a difference between the normal sets and the fuzzy sets. Then membership functions fully defines the fuzzy set. It can have operations also. So what are the operations of classical sets? As usual, not A. Containment, that is A is a subset of B. Intersection, A intersection B, then A union B. So we know in ordinary classical sets, we know how to draw the A union B. Isn't it? We know how to draw the A intersection. So like that. Then having all the methods of fuzzy sets also. So fuzzy sets. There will be a question like this. For ordinary sets, for complement, we know complement. If A is a set means A bar is a complement of the fuzzy set. So who does not belong to the set is complement of the crisp set. Who does not belong to the set is complement of how much percentage or how much membership function they are not belong to the set. That is a fuzzy function. They are not belong to the set. That is a set. So if A bar is equal to set of all X, A bar belongs to A or X does not belong to A. X does not belong to A, X does not belong to A. A complement. A means set of all X belongs to A. A bar means set of all X does not belong to A. Whereas in fuzzy set, it will be 1 minus how much it is involved in the set. That is 1 minus membership function. 1 minus mu of x. For example, I am giving an example of tall men. Fuzzy set consisting of the tall men. So it can a value 180 centimeter. The membership can be 0. 182.5, the membership can be 0.25. For 185 centimeter, it will be 0.5 like that. The values are given. For not tall men, the values will be 1 minus of the membership function. That is 1 minus 0. That is 1 for 180 centimeter. And 0.75, 1 minus 0.25. 0.75 for 182.5 centimeter like that. The complement will be defined. Hope you all understood the example given for the complement of the fuzzy set. Next one, containment. A is a subset of B. Like that. Which sets belongs to which other sets? That is, we can ask a question in crisp sets. Here in fuzzy sets, which sets belongs to other sets? If A is a subset of B, membership function of A should be less than or equal to membership function of B. As mu A of X must be less than or equal to mu B of X. So tall men 0, the membership value 0 for 180 centimeter, 0.25, like that it is defined. As a mu B, which is nothing but very tall man, the value must be equal or get less than or equal to. Like that the values are defined. For very tall man, actually tall man is a subset of very tall man. So 0, second line 0, if you go through the last line, 0 must be equal to the previous line 0 for 180 centimeter. Next value for 182.5 centimeters, the value for the very tall man is 0.06, that is less than the 0.25, like that it has been defined. This is the example for the containment. Next one, intersection. So before we are going with the classical fuzzy matrices and its applications, these are all the elementary methods, elementary definitions which the students should understand. Intersection. So A intersection B means set of all X. In classical sets, set of all X belongs to A and X belongs to B. In both the sets, if it is belong, then only we can say that it is an intersection. Whereas in fuzzy sets, if you want to give the intersection, it should be minimum of P1 of X and mu of X. That means tall man, the value is given as membership function is 0 for 165, 0 for 175, 0.0 for 180, 0.25 for 182.5, like that. And for average man, like that. The data are given. So what is the intersection of these two sets? Go through the sets. Whichever is minimum for 165 centimeter, which is minimum, both are 0. So 0 bar 165, which is minimum. Another one, 0. Next for 175 centimeter, which is minimum. Another one, next for which is minimum, which is minimum. 0 or 1, which is 0. The value we have to take for intersection is what? 0. Next, 0 and 0.5 for 180, 0. Which is minimum 0 and 0.5 for 0. Like that we have to define the intersection of a fuzzy set. Next you take 182.5 centimeters. Next you take 0.25 centimeters for both. So that is what we have to take. 0.25 as a we have to take. Next for 185, which is minimum, dear students, 0. You have to answer no. Generally the class will be interactive. Yes or no? Right. Next, 0 and 1. Here, whichever is minimum, 0. So, like that, the intersection of fuzzy sets. You all understood? Next, union. The next union is same way, but maximum of both the values. So, if you consider mu A of X and mu B of X, two sets. Okay. So, we have to write the union as how to define union of two sets, two fuzzy sets. It will be maximum of both the values. So, like that, if you go through this, so both the average, tall men and average men, maximum values are 0 for 165, 175 for 180 centimeter for 0.5. This is the basics of fuzzy. If you want to do your project or third year answer paper, if you want to learn, this is the basics. This is the membership function and support, core, normal fuzzy set. These are the basic definitions. Union operations or sets. If this is the basic, then you can fly in fuzzy anywhere. So we can do enormous problems of operation research. You know the concept of operation research? Operation research. Matrix, you can, coordinating with A and Python, we can do enormous problems in fuzzy matrix. We can do so many research papers. So that will come later. So this is the definition of the average, tall and average mean for union. Okay. Next, these are the basic properties of the crisp set of fuzzy sets. As usual, we know commutative property. This commutative property, all the first 9 properties go through for the classical sets as well as for the fuzzy sets. So you know the properties and we have studied. So commutativity property, A union equal to B union A, similar for intersection. Associativity property, distributivity property, idempotency, identity property. So these are all what properties of the crisp sets and as well as the fuzzy sets. Next we have transitivity. If A is related to B and B is related to C. Then we know the evolution A double bar is equal to the De Morgan's law, famous law, De Morgan's law, A union B the whole bar equal to A bar intersection B bar, A intersection B the whole bar equal to A bar union B bar. Then absorption law, then excluded Riemann law. So this law is specific law for fuzzy. A union A bar equal to X and A intersection A bar is equal to 5. 5 means 100. So these are the properties of fuzzy sets. So if you consider fuzzy set A is considered equal to fuzzy set B, mu A of X, the membership function should be equal. Then I can say that both the sets are equal. Is it clear? The membership functions are equal means then I can say both the sets are equal. Next we define the term called the cardinality. Cardinality of the fuzzy set, non-fuzzy set can be defined as mu A of x1 plus mu A of x2, etc. mu of x, that is summation sigma count, that is sigma of all the membership function. So if A is equal to 0.3, 0.5, 1 means cardinality of A is what? You have to add all the membership functions, that is 0.3 plus 0.5 plus 1 how much? How much cardinality of A? 1.8. What the cardinality of B is what? 0.5 plus 0.55 plus 1.52, 2.05 and so on. Next, the basic definitions is alpha cut. Alpha cut means two diagram we have a diagonal fuzzy number and two fuzzy number. So alpha cut is a very big definition. So for that we have to draw the diagram. If it's a whiteboard, I can can show you. So A alpha equal to mu A of x for delta equal to alpha. If you consider as x 1, 2, 3, and then set A is equal to membership function 1 point for 1 it is 0.3 and for 2 and 3 it is 1. So what is the alpha cut of 0.5 means whichever is bigger than 0.5, that is 2, 3 is alpha cut for 0.5. And for 0.1, there are what is the alpha cut for 0.1 here? All the 3 sets A, B, C, because 1, 2, 3, that is 0.3 is more than 0.1, 0.5 is more than 0.2, understood? Then 1 is more than 0.1. So all the membership functions are more than 0.1. Therefore, that set 1, 2, 3 will be the alpha cut for A.1. Similarly, what is A1? Alpha cut for membership function 1 is what? Only 3, because for the set 3 only, membership function is given as 1. Is it clear, everyone? Next, fuzzy set normality. A fuzzy subset of x is called normal if there exists at least one element x belongs to x, such that the membership function value is equal to 1. If the membership value is equal to 1, then it is called the normality fuzzy subset. Next one, height of a fuzzy set. It refers to the maximum membership degree within the set. So within the set, whichever is maximum membership, then I can denote that as called what? Height of the fuzzy set. So it represents degrees of truth or membership assigned to the most strongly associated element. So height of A is defined as what? Maximum of mu A of x. Mr. Fuzzy sets core and support. Support of A is one definition and core of A is another definition. Support of fuzzy set is defined as set of all Ax such that the membership function should be greater than 0 for every element x belongs to x. Similarly, core of fuzzy set is defined as set of all x. One membership function must be equal to 1. Of x should be equal to 1. Then I can say that it is a core of the fuzzy set. Now the topic comes fuzzy matrix theory. Do you all know the fuzzy mathematics? Fuzzy. It involves AI, applicable engineering, wherever ECE students, ECE, electronics and instrumentation engineering, all study this fuzzy topic as a core paper in their subject, engineering. Is it clear? So in that, mathematics plays a vital role in fuzzy. Using that fuzzy concepts, whatever we know in maths, like matrices, operations research, graphs, graph theory. So let us take a graph theory, last session. So we can have an implementation of fuzzy graphs. All the edges and vertices we can define, we can contain the membership value and we can draw fuzzy graphs. So for all the graph part, we can do the fuzzy graph also. So we can implement then statistics, fuzzy statistics is there. We know how to solve the Latin square design, numerical statistics concepts, testing of hypothesis, design of experiments. There and all research is there in fuzzy concepts. So fuzzy matrix is a mathematical representation. Actually, what is a matrix? Anyone define a matrix? It is an array of numbers. It consists of both rows and columns, isn't it? Same here also. Whereas the value consists of fuzzy matrix only in membership function. That is the values in between 0 and 1. It can be 0 and 1 also, but all the values in the fuzzy matrix should be in the decimals 0 to 1. So fuzzy matrix is a mathematical representation used in fuzzy logic and fuzzy set theory, whereas the elements of the matrix contains the value only the membership function that defines values from 0 and 1. So here 0 indicates means no membership and 1 indicates means full membership. The in between values from 0.1 to 0.9 represents what? What? I told this word already in this session. Partial uncertainty or partial membership. Okay. So values between 0 and 1 indicate partial membership. It's there last line no? Yes or no? Next. What is the history and definition of this? Fuzzy matrices. It is an extension of the classical method. We know how eigenvalues, isn't it? Normal eigenvalues. What is the procedure for solving eigenvalues? Normal classical mathematics, classical matrix eigenvalues. Eigenvalues and eigenvectors, you know, isn't it? Everybody studies mathematics. What is the first step for the matrix A given? If the matrix A equal to 3 cross 3 matrix given, what is the first step for finding the eigenvalues? The characteristic equation is the characteristic equation is determinant A minus sorry to my answer wrong. Determinant A minus lambda I equal to 0. Yes or no? Yes. So if the values are full, it is tough. Calculating the D1, D2, D3, the big cubic equation, then solving the cubic equation, we will get the eigenvalues. Yes or no? Right. With that, they won't leave us. They will not give full marks for us. So what we have to do? For all eigenvalues, we have to go for what? Eigenvector, isn't it? Yes or no? That is a big procedure again. Yes or no? So how to solve the eigenvector? See, in classical mathematics, all the values in the matrix A is whole number. I mean 1, 3, 1, 0, 1, 1, 1, 0, 1, yes or no? So for this whole number, finding the eigenvalues and eigenvectors by calculating is tough. Instead, we have a method in fuzzy. We can solve eigenvalues and eigenvectors for fuzzy matrix. That we have done. In 2009 and 10 research, what we do know, in that time, nobody found eigenvalues and eigenvectors for fuzzy matrix. So we searched, we worked on it also. So here, in that all the values are decimal in number. So the characteristic equation will be decimal equation. Solving the decimal equation, getting the eigenvalues in decimals like that, it will come in decimal only. Because by that time only research started 2007, 8, 9 and wherever was fuzzy topic only. So started hardly that time only. So there 2010, 11 and all, it has been started for the eigenvalues, transpose of a matrix, then inverse of a matrix. We know how to find the inverse of the normal matrix. That and all, no, we have done everything in what to say, fuzzy matrix also. So this is the issue of this matrix. So likewise, the basic operations on fuzzy matrices are there. So basic operation, addition of two matrices. We know the addition of two matrices A plus B. Isn't it? Just we add both the values and give the answers. Whereas in fuzzy matrices, we have to check the maximum membership. Whichever is maximum, we have to test for A11 in A matrix and B11 in B matrix. If it is a 2x2 matrix, means A equal to A11, A1U, A21, A22. Yes or no? Yes or no? So in that we have to compare A11 and B11. Whichever is maximum, that will be the answer. Similarly, A12 and B21. Whichever is maximum, that will be the answer. Like that, we have to write the addition of two matrices. In normal matrices, we have 2 plus 1, 3 plus 2, like that, we add and go. Whereas here, we have to check for the maximum position. So that is the addition of matrices. Then multiplication. Multiplication of matrices, what is the rule? Normal matrices, what is the rule for multiplication? A into B. A into B. Anybody? No. Row into column. Very good. Is there any rule for row and for matrix A and matrix B? Number of rows in column A must be equal to the number of columns in B. Then only we can multiply. Yes or no? Here in fuzzy matrices, that rule will apply as well as we have to go for the minimum maximum composition. We have to search for the maximum. In that maximum, whichever is minimum, that will be the answer for multiplication of two fuzzy matrices. So these are all the research. So normal matrices, normal product and addition only we know. Once the Zadeh developed in 1965, this fuzzy set theory. And the mathematics, fuzzy mathematics also got into the field. One topic, everything was introduced by one professor or one researcher day by day. By that time only it started. So now it is a full-fledged or it's a very big topic or very big, everything is over. Still more is there. But to take a subject, we can have the handful of problems are there in fuzzy matrices concepts. Then transposition. So these are the classical differences between the ordinary matrix and the fuzzy matrix. Then fuzzy relational matrices. Fuzzy relational matrices means it represents a fuzzy relation between elements. Each entry indicates the degree of relationship between rows and columns. So we know in discrete mathematics we have studied the relations. Yes or no? What are the properties satisfied there? Okay, I will ask you like this. What is the equivalence relation? What are the property to satisfy equivalence relation? Even professors can answer. The answer is there in my slide also. I can tell. But you should not sleep. What is the relation? Equivalence relation? Reflexive. A is related to A. Reflexive. Transitive. Similarly, A is related to B. B is related to A. Transitive. Yes or no? The same thing is nothing but what here? Fuzzy relational matrices. Next, intervalued fuzzy matrices. These are types of matrices. So intervalued fuzzy matrices. If the matrix defines for the interval A, B, or for the interval 0, 1, it represents what? The value 0 and 1 represents the membership function or uncertainty. 0 and 1 represents the membership values. So this provides the higher uncertainty such as diagnosis and financial assessment. So this is the definition of the intervalued and fuzzy matrices. This is the definition of intuitionistic fuzzy matrices. So till this lecture, we have seen only the membership function. Yes or no? We have for the matrix we have written only the membership function. If we input non-membership function also, x if we input a of x, that is membership function. Mu a bar of x, that means what? Non-membership function also. If you input mu a bar of a bar, intuitionistic fuzzy matrices. So it characterized by membership degree, non-membership degree. For example, the matrix A consists of A1 is 0.44. What is non-membership there? Matrix A consists of what is the non-membership there? 1 minus 0.4. This is a membership there 0.6. So like that the non-membership, if we include non-membership, also in the definition 0.6. Then it is called the intuitionistic fuzzy matrices. So effective in multi-criteria decision making, pattern recognition where hesitation is indeterminate is present. So these are the definitions of the intuitionistic fuzzy matrices. Hesitation is indeterminate is present. Next, so these are the definitions of the operators, operations, enhanced computational methods. Performs fuzzy matrices, enhanced computational methods. This research studies have introduced enhanced algorithms for performing fuzzy matrices into algorithms for accuracy. Non-linear programming approach. These methods utilizing non-linear programming have been developed to find the eigenvalues. I told you eigenvalues and eigenvectors addressing challenging traditional techniques. Generalized inverse. We know how to find out the inverse of a matrix. A inverse. 1 by modulus of A dot D. There is a formula for it. Here we are learning one concept called the generalized inverse in fuzzy matrices. It limits some of the complex fuzzy linear systems. Complex fuzzy linear systems. Next, I told you the definition of the intervalued fuzzy matrices. Which is fuzzy 0 and 1. Inclusionist fuzzy matrices means what? Membership together with non-membership. Both include values are inclusionary fuzzy matrices. Next, the new upcoming usage topic is the nucleosophic. Nucleosophic fuzzy matrices. What is this nucleosophic fuzzy matrices? This is one-step extension of inclusionist. That means it calculates membership, non-membership, and between intermediate value. That intermediate value can be anything. If membership value is 0.4. What is the non-membership value? 0.6. So that is membership and non-membership means it is inclusionist. In between, any value, even I can have 0.2 as an intermediate value. That intermediate value 0.2 may go for, we can take either for that is membership or for non-membership. So the matrix, the set consists of 3 values: membership, intermediate, or non-membership. That is called the nucleosophic fuzzy matrix. Then fuzzy eigenvalues and eigenvectors. This is the recent method employed in non-linear programming to determine fuzzy eigenvalues and eigenvectors, including precision and applications. So this is applications is stability analysis. So I have eigenvalues are all applying. Fuzzy eigenvalues are applying. Fuzzy eigenvalues are utilized to process the stability of the system under uncertainty, proving especially in engineering and control system. There is a paper in QB. So there we are using the eigenvalue problem in the course subject. Then algorithmic developments. New algorithms are being proposed to efficiently compute eigenvalues and eigenvectors in a large scale fuzzy matrices. Then optimization techniques using fuzzy matrices with solving pepper, isn't it? So we know in that transportation problem, programming, then assignment problem, and so on. So here supervised learning with fuzzy matrices, that is called stochastic gradient descent. That is reasons that is introduced optimization approaches. So now we have come to the applications of the fuzzy matrices, so which is our main topic. So here in optimization techniques, how the fuzzy matrices are useful. So some stochastic gradient for supervised learning in fuzzy matrices. So these methods are defined objective functions using means by error and incorporate constraints to ensure matrix elements remain within interval 0,1. So all the values in this supervised learning in fuzzy matrix also in the 0,1. Then in wireless networks, fuzzy matrices main application in wireless networks. That will electronics and communication engineering branch. They will do this wireless network. So how the phone and all coming no. So we are in here. If you press our number, our friend will receive a network coverage is there, no, that and all through wireless. So for there and all, we are applying fuzzy matrices concepts. So fuzzy matrices have been applied to optimize resource allocation in wireless networks by representing channel conditions, traffic load, and user requests within a fuzzy matrix framework. And this approach enhances throughput, reduces latency, and lower energy consumption. So if you use this fuzzy matrix concept in wireless network, it will be less power, less energy, and maximum profit method. Then decision making models. So we know how to use the decision making models. Here also fuzzy matrix area has been utilized to address decision making problems under uncertainty. For instance, in certain consumer products like mobile phones, fuzzy matrices model varying futures. So depending upon the futures of the mobile, then how GB will, photo camera, everything will check, then only will buy, So there and all, the concept of how much which will work, how much the fuzzy matrices value or fuzzy value will applicable. Next, fuzzy graphs. I told you now, just now. Fuzzy matrices plays a very good relationship, varying degrees of strength between nodes, enhancing the model of complex networks. Then applications, it is applied to social network analysis, biological systems, communication networks to capture uncertainty and partial relationship. So what is the recent research in fuzzy graphs doing going means? Lithogenic fuzzy graphs as explained the traditional graph framework allowing for the modeling of both complex systems with multiple attributes and degrees of membership. So these are the advances in fuzzy graph theory. Topological indices, development measures like this strong combination in fuzzy graphs aids in understanding network resilience and control. So what are the recent research in this? Advances in this theory, advances in the exploration of strong domination. As such, they have given domination graphs. Strong domination indices offers new perspectives on networks, new players and control mechanisms. Next, neural networks and soft computing. So now, artificial intelligence and neural networks, AIDS, data science, there is a vital role in all over the globe. So in that, fuzzy plays a vital role in neural networks. So if we input something and some process will do inside, then the output will come. That is a neural network. Okay. Integration of fuzzy logic with neural network enhances handling of uncertainty and intersection in data. Then, what are the applications of these neural networks? It is applied in pattern recognition. Pattern recognition means there is a called one number. What number is called? One phase number. That is a word ratio. So word ratio. So we can have pattern recognition. So using the pattern recognition, the membership values are defined and so our phase, the pattern of a product In pattern also we use that pattern recognition. So how the structure of the, for example, if it is a bottle means how the pattern of the bottle should be like this. Why can't it be the round shape? Like that the pattern we can modify through the fuzzy matrices. That is neural networks. And decision making process, where data ability is prevalent. Since I am working in engineering mode now, so I am giving you more examples for engineering applicable in, what to say this, fuzzy matrices and fuzzy concepts. Is it okay? This you have to know. Is it clear? Everybody should know the application of whatever we are studying. So then research. The study demonstrates effectiveness of fuzzy neural network in social media using the behavior analysis, including the design of personalized recommendation system. Next, engineering application. Structural reliability assessment. This fuzzy matrices are used to evaluate the reliability of the engineering structures by modeling uncertainties in material properties and loading conditions. In civil engineering, structural engineering, civil engineering, there is a loading and unloading values are there. In that, these fuzzy matrices concepts are used. Then control systems. It enhances the robustness of control systems, allowing for better handling of systems, uncertainties and non-linearities. Then research. In this engineering is fuzzy cognitive maps. That is mapping of the value to the another value. Cognitive maps in modeling complex engineering system, aiding in decision making and system optimization. So these are all the engineering applications of the fuzzy matrices. Then decision making analysis applications. Fuzzy criteria decision making, MCDA. Fuzzy matrix facilitates the evaluation of multiple conflicting criteria, aiding in selecting optimal solutions in conflict optimization scenarios. So it plays a vital role in the optimal solution, getting the optimal solutions, decision making analysis and all. Then supply chain management. Do you know the concept of supply chain management? What is that? So loading and unloading. So we are getting vegetables from. How we are getting vegetables? Follow. We are getting by nearby there is a shop. From that vendor we are getting it. So but from where they are getting free Coimbatore market, wholesale market. To Coimbatore market from each and every district. From the agriculture, from the each and every district. There will be a lorry moving. Each and every GST road or whatever. There will be a very big container. We will move, but with slow speed. If we go by the car, no, we won't go by the speed. We will move yes or no. So that is nothing but the logistics, supply chain management. So they will bring everything to the city, and from here they will take the logistics. I think that is called supply chain management. Here also the supplier selection and performance evaluation modeling uncertainties in supply chain parameters. So we'll go, chain aspects. It will move from there to come here. From here to it will go some other Hyderabad or something like that. That will go around. That is called supply chain management or the logistics. Then recent research in smart machine learning has enhanced decision making process, particularly in selecting products with varying features. Next one, medical application. So we have done a research paper in corona. Here corona using the fuzzy matrix. I have done one paper and got published for corona. So here disease diagnosis and classification. So for medical application, for the major disease like cancer or whatever, so we can apply our fuzzy values in order to calculate how much days this disease will be in the patient. How many days it will move from the application, it will go after that. We can do search in medical applications. So it assists in handling ambiguous and imprecise medical data, improving the accuracy of disease diagnosis and patient classification. Medical imaging. So we are taking the MRI scan that are not imaging or not. Fuzzy data monitor and fuzzy matrix aid in noise reduction and edge detection, leading to better visualization of medical images. So that is not day-to-day life we are applying the fuzzy concepts, but we do not know if it's all under fuzzy or not. Then recent research, the integration of fuzzy decision-making models in healthcare has shown promise in improving the diagnostic process and treatment planning. So if we give some medication to the patient, after some days, it will move after doing the another test. If it also that are all the research going on in this fuzzy matrix in medical application concepts. Then decision-making application, this we have done now. Image processing application, in that edge detection, noise reduction, then image segmentation. Fuzzy matrices enhance edge detection by handling uncertainties in pixel intensity variations, leading to more accurate identification of object. While drawing the engineering graphics and all, it will mark in pixels. There and all fuzzy matrices are using. Then noise reduction. In big factories and all, there will be a very big noise. Utilizing fuzzy logic, these matrices effectively reduce image noise while preserving essential features, improving overall image quality. Then image segmentation. Fuzzy matrices facilitate the partitioning of images into meaningful regions by accommodating ambiguity in pixel classification. In pixel classification, by doing the drawing, this fuzzy matrices will play a vital role. Then machine learning applications. Pattern recognition. Pattern recognition plays a vital role in fuzzy matrices. It involves machine learning models to process imprecise data, enhancing the recognition of complex patterns. Then a decision-making system, it leads to the model uncertainty and vagueness, leading to more robust AI systems. Then supervised learning. So here, recent advancement includes optimization approaches and structures gradient they said for learning fuzzy matrices, improving the accuracy of supervised learning models. Then medical image analysis. So as I told you already that techniques such as fuzzy edge detection, segmentation, improve the clarity and accuracy of medical images, aiding in the better diagnosis, they can apply the fuzzy matrices. What is an outcome of that? Implementing fuzzy matrix method has led to improve the detection rates of medical conditions, demonstrating their efficacy in clinical settings. Then financial application. Financial application also fuzzy matrices are employed to evaluate the financial risk, the modeling uncertainty. So we are BSc, SSC and stock exchange is there no. In stock exchange also, there are fuzzy matrices play a vital role in enhancing the robustness of the investment decisions. So in each company we can invest like that. Fuzzy matrices plays a vital role in risk assessment also. Then portfolio optimization. So for this ministry, what portfolio we can select? Fuzzy matrices concept will apply. Cooperative fuzzy logic allows for the handling of the ambiguous data, aiding in the selection of optimal assets mixes under uncertain market conditions. Then credit scoring. Fuzzy matrix approaches improve the assessment of credit worthiness, accommodating the various financial data. So in we are using the card, isn't it? What card? Credit card and debit card. No. In that there is one scoring called CIBIL scoring. So for CIBIL score, how to maintain the credit worthiness. So we have purchased, we have to pay the thing, then the CIBIL score will higher. You know or not? I don't know because I'm the best CIBIL scorer for the credit card. So in that, no, what's it? Fuzzy matrix, we don't know how it's applying, but it's applying in credit card. So we can say that in financial also, our fuzzy matrix plays a vital role. Okay? Then supply chain management application. I told you already the supply chain, that is a supply selection, fuzzy matrix, facilitate evaluation of suppliers by considering multiple criteria under certainty leading to the informed and reliable selection decisions. So fuzzy AHT and multi-Mura method, these are the two methods, enables comprehensive assessment of risk and benefits with the suppliers, optimizing supply chain performance. So then sustainability risk management. So whatever we are doing, it will be sustainability. So if we do research or if we do study, it will be sustainability there. So in that fuzzy frameworks, sustainable risk management is there, combined with the digital twin technologies, enhancing assessment and management of sustainability risk in supply chain, promoting resilience and efficiency. So these are given already the explanation in the supply chain management applications. Then economic modeling with fuzzy matrices, fuzzy input-output models. Fuzzy matrices utilized to handle uncertainties in economic input-output models, allowing for more flexible and realistic representation of economic activities. And fuzzy linear systems, applicable in economics, model and analyze economic system with inherent uncertainties, providing more robust solutions. Then dynamic economic models, Della economics under economics incorporating fuzzy logic into dynamic models, for the analysis of economic behaviors over time under uncertainty, enhancing the understanding of the economic dynamics. Then artificial plays a main role nowadays. Please, you can listen to this. Fuzzy matrices and artificial intelligence. Fuzzy matrices are utilized to model input and output fuzzy vectors, enhancing learning algorithms applied to uncertainty. So these studies gives the proposed optimization approaches based on stochastic variant research for learning fuzzy matrices. Then decision making system we have seen so many times. Then clustering and pattern recognition. Fuzzy matrix enhance clustering algorithms by allowing data points to belong to multiple clusters with varying degrees of membership. So by applying the pixel varying in number, we can check our face or we can do some pattern. So by applying the varying degrees of membership, improving pattern recognition in complex data sets. Techniques such as clustering ensembles based on fuzzy matrix self-enhancement have been developed to yield more accurate and robust clustering results. Then this is an integration with the neural networks. Neuro-fuzzy system combining neural networks with fuzzy logic. Neuro-fuzzy system utilizes fuzzy matches to represent and process uncertain information, enhancing learning capabilities. Okay, so this integration allows the handling of imprecise data, the extraction of interpretable rules from neural networks. So these are the deep learning enhancement, spiking neural networks. These are all the applications of the fuzzy matrices. Then fuzzy cognitive maps in medical diagnosis. So these are the methodology, outcome, fuzzy cognitive maps. So fuzzy matrices, day-to-day life we are applying, even in medical diagnosis also. Integration with the neural networks. Challenges in fuzzy matrix theory. Fuzzy matrix operations involve large-scale systems, the computationally intensive, like that. Then non-smooth operation, handling high-dimensional data. So these are all the challenges in fuzzy matrix. So for this, we have to find out the answers so far. Future directions in fuzzy matrix. So integration, machine learning, development of advanced optimization algorithms, current going topics, research topics in fuzzy matrix, expansion into new application domains, conclusions and references. Thank you so much for your patience. So I hope I have covered all applications of fuzzy matrix. Now it's useful to you or not, I don't know. But once if you want to pursue a doctorate in regarding PhD, fuzzy will be a very major role in all aspects. Thank you so much. Thank you so much, ma'am, for meeting me. Any questions, any doubts I have? One more session is waiting for you. Doubts or no doubts? Thank you so much. Doubts or no doubts? Thank you so much. From pen drive. Yeah. अभी लैपटॉप पे तो फोटो रखी है
ஒரு நிமிஷம் இரு.
heard complex analysis. So you have done one course at least? Yes? Complex analysis. Okay. You have done one course at least. Students I'm asking. So what is complex analysis? Very difficult question, no? Okay, once you hear the word whoever has done complex analysis, what is the repeated word you hear in that? Or what is the one word or the first word? Analytic matrix or analytic polynomial or analytic number, what you have read? Analytic functions. What is an analytic function? Okay, let me not be technical. Right. Yeah. Why should we learn complex analysis? Have you ever thought of it? You learned UG level, PG level complex, no, suppose. Why did you learn? Real analysis was enough? No. You already know the effect of real analysis. That was more enough. Then why separately complex analysis? You should think. Why should you really learn complex analysis? Just because it is there in the syllabus you should learn, right? But complex numbers are isomorphic to R2. So it's enough to read real numbers, real analysis, right? Then why complex numbers, complex analysis, right? Madam, can I know when should I stop? Okay. I'll try to stop. Maybe I'll try. Because I was allotted 45 minutes, I prepared accordingly. Right. Okay, so let me not waste time. I understand that research scholars are attending even in online. So, okay. Complex analysis mainly deals with studying complex valued functions of complex variables, right? Complex valued functions of complex. Then why real analysis is not enough? Because there are so many ways in which complex valued functions differ from real valued functions. So many ways. Real analysis is not so big to handle complex analysis. It's not enough, right? One simple example I will tell you. Is 2 bigger or 3 bigger? 3. Is 2 plus I bigger or 3 plus I bigger? Have you ever thought? Given two complex numbers, have you ever done which is ascending order, descending order? Or which is bigger, which is smaller? Why did not you do? Such simple question. You immediately told whether 2 is bigger or 3 is bigger, 2 is bigger. Okay, you think. If 3 is bigger than 2, can we say 3 plus I is bigger than 2 plus I? Or have you ever come across arranging complex numbers? This is one of the main difference between real numbers and complex numbers. So several such. Okay, so the topic of my next question. You know, in a real line, where will you put infinity? At the right hand one, left hand one. In complex plane, where will you put infinity? So many real lines are there, x-axis, y-axis. Any line passing through origin can be treated as isomorphic to real line, homeomorphic to line. For how many infinities? More than one? What is infinity in complex numbers? Think of it. First one I told, what is ordering? Can you order any two complex number? Second thing I told, where will you mark infinity? Okay. And then, if x is real, modulus of x means plus x if x positive or 0, minus x if x negative. Can we do the same thing in complex numbers? Can we say mod z is z if z greater than 0 and minus z if z less than 0? What do you mean by z greater than 0 and z less than 0 when z is complex? Not defined. So I give you 3 places where complex analysis or complex numbers differ from real numbers. So real analysis is not enough for us to learn complex analysis. This is one example. Okay, so one of the research area in complex analysis is geometric function theory. The very word tells that we deal with the geometry of functions. Geometry of what? Every function, when I say functions, preferably analytic functions in complex analysis, complex plane, it will have a range, right? So how will the range look? The range will have some shape, right? I don't want to go more technical. So studying about range of complex valued function or analytic function is called geometric function theory. Geometric. I am interested in geometry of the range of an analytic function, right? That gives very beautiful theory. It's called geometric function theory. And in geometric function theory, when the analytic functions are one-to-one, the fancy name for one-to-one function in complex analysis is univalent, right? Theory is more rich. It all started about in 1916 with the famous conjecture, which was unsolved till 1984. So how many years? 68 years, I think, right? 84. And that led to the development of the subject tremendously, right? A conjecture. And that conjecture is very simple to understand, a very beautiful conjecture, right? Anyway, and the counterpart of univalent function theory is your harmonic univalent mappings, which was initially studied by, harmonic mappings were initially studied by differential geometers, right? And then in 1984, there was a paper by Clooney and Searle-Small, which led to the birth of harmonic univalent mappings, and we complex analysts got interested in it, and there are many things done. Hence, on the theory, and I don't think I can discuss any problems, right? I didn't have time to prepare any problems in harmonic univalent, but I can tell you if you want, right? Yeah. So outline of my talk, I'll be just touching on analytic functions, univalent functions, harmonic mappings, Schwarz lemma for harmonic mappings, Landau and Bloch constants, of course, for harmonic mappings, and finally univalent harmonic mappings. Analytic functions. There are several types of subsets in complex plane. Particular type of subsets on which functions are defined are very interesting, especially simply connected domain. A domain in a complex plane, or an open connected set in a complex plane is said to be simply connected if it doesn't have any holes. It doesn't have any holes in it, right? Or technically speaking, a domain D in a complex plane C is said to be simply connected if its complement with respect to the extended complex plane C union infinity is connected. So even BSc students, I have indicated an infinity here, just to see whether any book shows you where infinity is in complex plane, right? Or how do you denote infinity in complex plane is very interesting. It is very interesting to know, right? An example of simply connected domain is open unit disk set of all complex numbers whose modulus is strictly less than 1. Other examples are right half plane, left half plane, upper half plane. These are examples of and then we always consider functions defined, analytic function defined on open unit disk for some reasons, right? So analytic function. So let C denote a complex plane and D denote a domain on the connected open set, an open connected subset of C. A domain, by a domain I mean an open connected subset. Open means complement is closed and connected means single piece. It cannot be written as union of two open sets. A function is said to be analytic at a point z0 if two things. Number one, it is differentiable at z0 in the sense of complex variable. Number two, you can find a neighborhood around z0 where it is differentiable, right? So if it is differentiable at z0 and there is a neighborhood of z0 where it is differentiable. I compare complex analytic function with agarbatti. When you light an agarbatti, not only the place where it is lighted is fragrant, but you can definitely get some places, at least in the room when you enter, fragrance will be felt, right? So you can, this is my idea, I don't want you to take that, right? Right. But what do you mean by analytic function in a domain? A function f is said to be analytic in a domain D of complex plane if it is analytic at every point in the complex plane. That's usual, from one point you can extend it to the entire set, right? Yeah. Now, what is the connection between analytic function and partial differential equation? Can we interpret an analytic function as a solution of a partial differential equation? Yes. You know, if a function is analytic, it will not have z bar. It will not have z bar. You will have now, whoever done a course in complex analysis, if you look at all the examples of analytic functions, only z will be there. Z square, e power z, polynomial, sine is z, cos is z. You will never find a function, example of an analytic function with z bar, because analytic function cannot have z bar. So once a function cannot have a variable, what does it mean? Derivative with respect to that variable should vanish. You know, the derivative with respect to that variable should vanish. So a function which satisfies an analytic function, if f is an analytic function that in a domain D contained in complex plane, it satisfies the partial differential equation dou f by dou z bar equal to 0. That is, analytic functions of f are necessarily independent of z bar. Actually, this is, you know what is Cauchy-Riemann equation. If f equal to u plus iv is analytic, dou u by dou x equal to dou v by dou y, dou u by dou y equal to minus dou u by dou y equal to minus dou v by dou x is a partial differential equation. I mean, actually partial differential equation. This pair of partial differential equation or this pair of Cauchy-Riemann equation can be represented as a single equation which is shown here, dou f by dou z bar equal to 0. Actually, this is another way of writing Cauchy-Riemann equation, right? As a single equation. Normally, Cauchy-Riemann equation will tell a pair, right? Ux equal to vy and uy equal to minus ux. Combine, I can tell like this, right? Or analytic function will not have z bar; they will be independent of z bar. Next, I recall what is univalent function. Univalent functions are nothing but a one-to-one complex valued function. When do you say a function is 1-1? Whenever I have two distinct points z1 and z2, their images are under an analytic function should be distinct, right? So technically, let D be a subset of C. It may be the whole C also, right? That's why the notation. A complex valued function f from D to C is said to be univalent if it does not assume two values and same value twice. If it does not assume same value twice. For example, if you take f of z equal to z square, right? Take x equal to minus 2 and plus 2, same value you will get. I can very well take real numbers, right? But at the same time you take z, it's not so, right? Or whenever I have two distinct points z1 and z2, their images should be distinct. F of z1 not equal to f of z2. Put in other words, if f of z1 and z equal to f of z2 for any two z1 and z2, then z1 equal to z2. I think the second condition only we use most of the time in proving one-to-one, right? And the name univalent function we give to distinguish between real valued 1-1 function and complex valued 1-1 function. Once you have the class of, the notion of univalent function, right, we can talk about a collection of univalent functions in addition to some other conditions, right, that I denote by yes, right. So this is a basic object for anyone working in univalent function theory. The class S of all normalized, analytic and univalent functions defined on the open complex plane, open unit disk in the complex plane, that is S. S is denoted by set of all functions f from unit disk. The symbol delta here stands for open unit disk. Set of, I told you, no, open unit disk, I told you here. Yeah, this one, I'm using this one, right? So class S stands for collection of all analytic functions defined on open unit disk which are univalent, plus f of 0 is 0, f dash of 0 is 1, right? And whenever you have, another way of defining an analytic function at any point is a function f is said to be analytic at a point z0 if it has a Taylor series expansion for every point in the neighborhood of z0. This can be very well treated as definition of an analytic function. We don't want that definition of let z0, there is a neighborhood at z0, etc. If it has a Taylor series, it's analytic, right? And particularly when the z0 is 0, the Taylor series will look like a0 plus a1z plus a2z square plus dot dot dot, right? So, but particularly if f is in S, then f of z can be written as because origin is very well inside the unit disk. It can be expanded as z plus summation n equal to 2 to infinity a n z power n. Okay. Now, why should it start with z plus, right? And where is the constant term? F of 0 equal to 0 implies constant is 0, and f of f dash of 0 minus 1 equal to 0 means f dash of 0 equal to 1, which makes a1 equal to 1, because a1 is actually f dash of 0. So, you know, if you remember the Taylor series expansion, an's are given by, you know, that integral formula, you know, right? Okay, so that is why here constant term is absent and z is 1, right? Okay, why should we need that condition? You know, such condition f of 0 equal to 0 and f dash of 0 equal to 1 will not affect the univalency of f. If f equal to a0 plus a1z plus a2z square etc. is univalent, then f of z minus a0, which is equal to a1z plus a2z square plus etc. is also univalent. Also, if a1 is not equal to 0, I can very well divide by a1. F of z minus a0 all divided by a1, which is equal to z plus a2 by a1 z square, I hope I am right, plus a3 by a1 z cube plus dot 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 will still remain univalent. So how is the series starting? Z plus. That only makes me to have series in this form. But instead of having a1 by a2 by a1, a3 by a1, I call it some other a, right? Okay, so that is the reason why we have this normalization. F of 0, 0 and f dash of 0 equal to 1. It will not affect the univalency of the function. Okay, coming to the main topic. And a lot of research I have done on analytic univalent function theory. It all started with a conjecture post in 1916 by Bieberbach that these ANs you find here in modulus cannot cross n. Right? Modulus of AN will be always less than or equal to AN for n greater than or equal to 2. In fact, mod A2 less than or equal to 2 was proved by Bieberbach himself in 1916, and in the footnote of the paper, research paper which he wrote, he made a comment. In general, AN less than or equal to n for each n greater than or equal to 3. Right? And okay, you know, as math students, whenever you come across an inequality, you should ask a question, where will equality come? Where will equality come? Then why do you put, if A less than or equal to B, less than or equal to, so it may be less than or equal to, when will equal to come? You should address, any math student should address, when will equality come, right? And that is very much important for people working in geometric function theory. So A2 less than or equal to 2 means, for which function A2 will be 2? There is a famous function called Kobe function. K of z equal to z plus 2z square plus 3z cube plus dot 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 z by 1 minus z the whole square. For this function, A2 will be 2, A3 will be 3, A2025 will be 2025 dot dot dot, right? So for this is called a sharp extremal function for the class S, because the equality occurs there. Okay, yeah. So and so that's about S. Now in 1984, Clooney and Sealswald wrote a seminal paper, harmonic univalent mappings, where they introduced harmonic mappings and tried to study or tried to build the analog of univalent function theory there, right? So what is harmonic? Harmonic mappings are not new to anyone who have done first course in complex analysis. You very well know that. What is a harmonic function? You know very well. A function u, which is twice continuously differentiable, is said to be harmonic if dou square u by dou x square plus dou square u by dou y square equal to 0. I say function u is a function of a real valued function of two real variables, right? Or it satisfies Laplace equation del u equal to 0, right? Now there is a connection between an analytic function and harmonic function, which you know very well. What? If f of z equal to u plus I, or if f equal to u plus iv is an analytic function, then u and v are harmonic. U and v are harmonic. This is a result done in UG level of complex analysis, right, in the first course itself, right, meaning u and v satisfy Laplace equation, right? So that's what I have recalled here, real valued harmonic mapping. Let omega be an open subset of complex plane C. A real valued function u from omega to r is harmonic if u is C2 of omega. What is C2 of omega? The set of all functions with continuous partial, second and first order partial derivative, meaning ux will be different continuous, uxx also will be continuous, uy will be, when I say ux, dou u by dou x, dou u by dou x is continuous, dou square u by dou x square also continuous. Similarly for the mixed partial derivative with respect to y, with respect to y, derivative with respect to y, plus it satisfies the Laplace equation del u equal to 0, namely dou square u by dou x square plus dou square u by dou y square equal to 0, right? And such a function will be, or in other words, a C2 solution. By C2 solution, a function in C2 is called real harmonic function, right? Now what is complex harmonic function, complex valued harmonic function? Let omega be an open subset of complex plane. A complex valued function f equal to u plus iv is called harmonic if the coordinate functions u and v are real harmonic. See, f is having two real functions, u and v. If both of them are real harmonic, and that is del f equal to 0, then I say then I say f is complex valued harmonic function, right? Are you understanding? Please understand that the f equal to u plus iv, which I mentioned here, such that u and v are real harmonic, need not be analytic. Need not be analytic. You can have complex valued functions f of z equal to u plus iv, where u and v are harmonic, but f is not analytic. Please understand the result. If f equal to u plus iv is analytic, u and v are harmonic. But just because u and v are harmonic, f need not be analytic. Very simple example is z bar. Z bar. Whenever you want some function which is not analytic, easiest thing is taking functions with z bar. Don't go for those which have poles and all, 1 by etc. Right? Z bar. What is the real u in z bar? X. What is v in z bar? Minus y. Obviously uxx is 0, uyy is 0. You can check this. So it's harmonic, but it's not analytic. Z bar is not analytic. Right? So there is a difference. You must understand. What is the difference here? If omega is an open subset in the complex plane, a complex valued function is called harmonic if coordinate functions u and v are real harmonic. U and v should be real harmonic. Whereas for real valued harmonic function, I had a real valued function which is harmonic. Here I want both of them to be harmonic. Remark, the study I'm telling you omega is open subset. Think why we always take open subset. Right? Why don't we take closed subsets? Next, remark. The study of analytic functions and harmonic functions are carried out often on simply connected domain. Though I have defined this for omega, which is arbitrary open subset, I normally consider simply connected domain. I think this is the second time I am telling. There is a reason. I'll come to it later. Right? Why it should be study only functions with the domain as simply connected domain and not any other domain, any other subsets. And in particular, that too, unit disk is enough. Unit disk is enough. Right? That is why. That I'll tell you why later. Right? A planar harmonic function or simply a harmonic function is analytic on a domain if and only if you already know the sufficiency condition in Cauchy-Riemann equation. U and V are harmonic conjugates, that is U and V are C2 function and satisfy CR equation. This was the sufficient condition, right? Harmonic function is simply harmonic, is an analytic function. When will you say harmonic function, analytic function? It not only satisfies C2 CR equation, but it should have continuous second order partial derivative, right? Now, what is the close relation between analytic function and harmonic function? I told you already, right? The real and imaginary parts of an analytic function in an open set are harmonic. If f of z equal to u plus iv is analytic, then both u and v are harmonic. In particular, every analytic function f and its conjugate f bar are harmonic. So, what is this? Analytic function will not accept z bar, but harmonic function will accept the conjugation, right? I told you one result. If if f is analytic, then it is independent of z bar. Can we tell similar thing for harmonic? Yes. If f is harmonic, then dou f by dou z, f is z, is necessarily independent of z bar. It will not have z bar. You know, that's very obvious because you see this del f equal to 0 means dou square z by dou z bar equal to 0. Or you can interchange dou square by dou z bar dou z equal to 0. That means what? Partial derivative with respect to z bar is 0. Partial derivative of z with z bar is 0. Or partial derivative of z bar with respect to z is 0. Right? That is what is written here. Fz is necessarily independent of z bar. What do you mean by that? Dou by dou z bar of dou f by dou z equal to 0. Right? Dou by dou z bar of dou f by dou z equal to 0. That means dou square f by dou z bar equal to 0. Right? So it is an interpretation of harmonic mapping. If f is harmonic, dou f by dou z will not have z bar. If f is analytic, f will not have z bar. F will not have z bar. Right? Some remarks. A function f in planar domain is harmonic in it if and only if fz is analytic there. Fz should be analytic. If and only if it is harmonic, right? Further, if f is analytic, then what is f is that? What is the partial derivative? It becomes the original derivative itself. If f is analytic, dou f by dou z will become the derivative itself. And you know the collection of harmonic mappings are bigger than the collection of analytic functions. Meaning every analytic function is harmonic, but there are harmonic functions which are not analytic. Right? Okay. Another one important class of mappings is conformal mapping. This is also one of the topic which you learn normally in the first course of complex analysis, right? And the famous definition is an analytic function f which is univalent. So I take univalent function which is said to be conformal at a point z0 if it preserves the angle both in magnitude and direction at z0, but in every pair of smooth curves gamma 1 and gamma 2 passing through z0. This is a normal definition we see. And there is one interesting condition. If f is conformal at a point means f dash at that point should not be 0. That is same as telling f is univalent, right? And I was repeatedly telling it's enough to consider open unit disk instead of arbitrary simply connected domain in the complex plane. Why? The reason is Riemann mapping theorem proved somewhere in 1880s by Riemann, right? There exists a unique conformal map f of the unit disk delta onto a simply connected domain except the whole plane. The simply connected domain should not be entire plane. From the unit disk, I can find a conformal mapping to any proper simply connected domain of complex plane. Any proper simply connected plane of complex plane, meaning not the whole C, except the whole complex plane, such that for a given point z0, f of z0 and the argument of f dash of z0 takes given values. In other words, this line will be like f of z0 will go to 0 and f dash of z0 greater than 0. In some books, that will be the statement of the Riemann mapping theorem. And what is the advantage of this Riemann mapping theorem is that, because of this Riemann mapping theorem only, it is enough to study analytic functions or harmonic univalent functions defined only on open unit disk. I don't want to consider any other arbitrary domains. Right. There are so many. I don't want. It's enough always to consider the domain of analytic function, univalent functions, or harmonic univalent function to be open unit disk. Right. That's one great advantage. I can dispose all other possible domains. Right. And this is a theorem for conformality. Suppose f is analytic, and if derivative at z0, if f dash of z0 not equal to 0, then f is conformal at z0. See, conformal is same as univalence. So if f dash of z0 is not equal to 0, I can conclude f is univalent. The converse is also true, right? Meaning what? If you have a function f such that it is conformal, then the derivative of z0 is not equal to 0, right? What are examples of conformal mapping? 1 plus e power z is conformal everywhere. Look at the derivative e power z. It never vanishes. That's the beauty of e power z. It will never vanish anywhere, right? Z square. It's conformal everywhere except at the origin. How do you find it? Just take the derivative and put equal to 0. Whatever you get, there and all it won't be univalent. Z square, what is the derivative? 2z. So wherever 2z is vanishing, it is not conformal. So where does 2z vanish? Only at z equal to 0. So z square is conformal except at the origin. Similarly, cos pi z is conformal everywhere except at integer points. You please think why this is. Right? Answer is sin n pi equal to sin x equal to 0. If z equal to 0, if only z equal to n pi. That is integer multiple of pi. And why did I tell sin? Though cos is here. Please think. Z plus 1 by z is conformal at all points except at 0 plus or minus 1. Just find the derivative and equal to 0. You will get a quadratic equation. Wherever it is 0 is 0 plus or minus 1. At those points alone, it is not conformal. Right? And conformal mappings are widely applied in to studying electrical field problems or thermal fields problem, etc. Right. Now, we saw what is a complex valued harmonic mapping. One advantage is that if you are working on a simply connected domain, right, every harmonic function on a simply connected domain has a representation f equal to h plus g bar, where h and g are analytic. Right? The representation is unique up to an analytic constant. Right? This h is called analytic part of f and g is called coanalytic part of f, not g bar. G is called coanalytic part of f. Right? And once I say h and g are analytic, they also will have Taylor series expansion. I can always take h of z as summation n equal to 0, a and z power n, and g of z as summation n equal to 0, b and z power n. Whenever I'm working in unity, open unit list, mod z less than 1. Right? So please remember, harmonic mappings, when defined on simply connected domains only, can be written as H plus G bar, where H and G are analytic, hence they have Taylor series expansion about origin as shown, right? And what will be harmonic univalent mapping? Of course, this for any harmonic mapping need not be univalent, right? Let omega be a simply connected domain. A complex valued function f from omega to is said to be harmonic univalent mapping if it is number one harmonic, number two one to one, univalent, meaning f of z1 not equal to f of z2 implies z1 not equal to z2. I'm sorry. Whenever z1 not equal to z2, f of z1 not equal to f of z2. That's what I have written here for with z1 not equal to. Examples of harmonic univalent mappings: f of z equal to z minus 1 by n z bar, when where z is in unit disk, and z plus 1 by n z power n. Please note that in second example there is no bar. Don't think it is a mistake. This is the example. It is z plus 1 by n z power n. Right? Yeah. Jacobian. Right. The Jacobian is nothing but the counterpart of derivative of analytic function. Right. We know that if f is analytic, it is differentiable, meaning f dash exists. Right. So the Jacobian of a complex valued harmonic mapping f from omega to c is defined as what? Jf of z equal to modulus of fz of z, that is dou f by dou z, dou fz of z the whole square minus fz bar of z the whole square, that is dou f by dou z the whole square minus modulus of dou f by dou z bar the whole square, right? And particularly if f is h plus g bar as a canonical representation, your fz will be h dash and fz bar will be g dash. So I can write jf as jf of z equal to modulus of h dash of z the whole square minus modulus of g dash of z the whole square. Further, if f is analytic, what will happen? This g will become 0. You know, if f is analytic, if you have a harmonic function h plus g bar, what do you mean by f is analytic? G is not there. Co-analytic part will be absent. Therefore, in the above example, it will be only mod h dash of z whole square. But because f equal to h, f dash is same as h dash, or h dash is same as f dash. Thus, Jacobian is mod f dash of z the whole square, right, for analytic function. Now, using Jacobian, how will you decide univalence of a function at particular point or in a neighborhood of a particular point, right? A harmonic function f is locally univalent in a neighborhood of z0 if and only Jacobian is not equal to 0. So this was stated and proved by Levy, hence it is called Levy's theorem, very useful theorem in deciding the univalence of a harmonic function, right? That is, f is locally univalent in a domain if and only jf of z not equal to 0. See, practically it is not possible for us to check for every z1 and z2 in the domain whether f of z1 equal to f of z2 whenever z1 equal to z2, or f of z1 not equal to f of z2 whenever z1 not equal to z2. There are uncountable number of points in the domain, right? Hence, this theorem of Levy will help us to decide whether a given harmonic function is locally univalent or not. By local univalence, I mean univalence only at a point and nearby points, that is in a neighborhood of that point, right? So, to check whether f is locally univalent or not, just find out the Jacobian. How to find Jacobian? Just this, find out h dash, find out g dash, take the modulus square and subtract, right? If it doesn't vanish at a particular point, it is univalent there, locally univalent there, right? And because of the Jacobian, we can categorize, or because of Levy's theorem tells that jf not equal to 0, right? Remember, jf of z is a real quantity, it's a real number, modulus of h dash of z minus g dash of z whole square. And when I say jf of z not equal to 0, it's a real number. It may be positive or it may be negative. It may be positive or it may be negative, right? If you have a non-zero real number, either positive or negative. I say the given harmonic mapping is a diffeomorphism if it is univalent, it's a C1 function, meaning derivative is continuous, and jf not equal to 0, Jacobian not equal to 0. It is orientation preserving or sense preserving if further, that is addition to diffeomorphism, Jacobian is positive. Jacobian is positive. And it is orientation reversing or sense reversing harmonic map if its diffeomorphism and Jacobian is negative. Right? The Jacobian not equal to 0 gives two cases. It may be positive or it may be negative. If it is positive, if the Jacobian is positive, I say the map is sense preserving. Normally they use the word sense preserving. And if it is negative, I say it is a sense reversing. And normally there is no need to study about sense reversing because If f is sense preserving, minus f will be sense reversing. So it's always enough to study about sense preserving harmonic mapping. Next, an important quantity related to Jacobian or derivatives is what is called dilatation. Dilatation. Let's see what is the motivation for defining dilatation. Jacobian, as we defined earlier, jf of z equal to modulus of h dash of z whole square minus modulus of g dash of z the whole square. Pull out h dash of z whole square outside, right? Of course, if you are supposed to pull out, it should not be 0, right? Because I am dividing inside. Okay, we'll see. Already I am assuming jf is greater than 0. What is the advantage when jf is greater than 0? This is greater than 0. I mean, right? H dash of z greater than modulus of g dash of z. Modulus of h dash of z greater than modulus of g dash of z. But mod g dash of z is greater than 0. Modulus is greater than 0. So it is guaranteed that modulus of h dash of z is greater than 0. See, these minute things you must think when you do mathematics, right? I am taking some h dash of z whole square 0. What is happening? It is coming in the denominator. You know, as mathematicians, we should not have 0 in the denominator. You know, so what is the guarantee? H dash is not equal to 0. Only then you can divide, right? That is coming from here, right? Jacobian is positive, I am assuming here. Jacobian positive means, please see here, modulus of h dash of z minus modulus of g dash of z 0, greater than 0. That means modulus of h dash of z whole square greater than modulus of g dash of z whole square, which is positive. Therefore, mod h dash positive. Mod h dash positive. So I am guaranteed that modulus of h dash is not equal to 0. So I can pull it out. Right. Now you see the ratio inside. There is a term g dash by h dash. I take it as omega. Right. It is an analytic function. It's an analytic because I already h is not equal to 0. G is 0. G is analytic. H is analytic. Quotient of two analytic functions are analytic provided denominator is not equal to 0. So omega is analytic. No problem with that. Moreover, mod omega is less than 1. Why? Because one more thing you see, jf greater than 0 means mod g dash less than mod h dash. Please, you can compute from here. Jf greater than 0 meaning mod h dash square greater than mod g dash square, or mod g dash square less than mod h dash square, or mod g dash less than mod h dash, or mod g dash by mod h dash less than 1. Right. Hence, I have Jacobian mod g dash by mod h dash less than 1, but I am calling mod g dash by h dash as omega, so mod omega less than 1. Right. These are the properties of omega. Right. Also, by cross multiplying, I get g dash equal to omega h dash. Right. And this function omega, what I get newly using h dash and g dash, is called dilatation, and it plays a very important role in the study of harmonic univalent mappings. Okay. Yeah. Now, Beltrami equation and Cauchy regular mapping. A complex valued function f, for a complex valued function f, right, the equation fz bar equal to omega fz, where omega in modulus is less than or equal to k, is called Beltrami equation, right? And remark is what if f equal to express d bar is harmonic, then Beltrami equation is same as d dash equal to omega h dash. Okay, that's nothing to understand. And Cauchy regular mapping, a complex valued function is said to be Cauchy regular if it satisfies Beltrami equation. Any complex valued function which satisfies Beltrami equation is called Cauchy regular mapping. Right, like harmonic mapping satisfied dou square by f by dou z bar equal to 0, similar to that. Right. Critical points. Already you know in UG level you would have found out what is critical point. Points where derivative does not vanish is called or vanish is called critical point. Similarly, if u and v are C2 functions, the point x0 y0 where ux equal to 0, uy equal to 0, derivative should be replaced by partial derivative equal to 0 is called critical points. Right. And the points which are not critical are called regular points. Right. Yeah. I'm sorry. Yeah. Okay. Now, okay, Levy's theorem we saw. Yeah. So Levy's theorem tells that if Jacobian is not equal to 0, it is univalent, right? Yeah. Now, what is critical point for a harmonic function, right? Critical for a harmonic function f, the set of critical points consists of those points at which f is not locally univalent. So suppose you are interested in finding points where f is not locally univalent. It is enough to find critical point. What are critical points? Those points where Jacobian becomes 0. Those points where Jacobian becomes 0, right? I mean, here I have made a remark. Okay, right? Critical points are those points where Jacobian becomes 0. Points where Jacobian doesn't become 0 are the points where it is harmonic function is univalent, right? So if you want to find the points where a given harmonic function is univalent, take the Jacobian, equate it to 0, and delete all those points. At all remaining points, it will be harmonically univalent, right? Now, given two harmonic functions, and suppose we add or compose, will the result be harmonic or not, right? You know pretty well, analytic, if you have two analytic functions f and g, f plus g will be analytic, f composite g also will be analytic. F plus g is analytic, f plus composite g also analytic, hence it becomes a vector space, right, or linear space. But product of two harmonic function, the usual product of two harmonic function need not be harmonic. Example, you take x and x square. You can check whether x is harmonic and x square is harmonic, but the product will be x cube will not be harmonic, because once you differentiate it is 3x square, next time 6x, right? It will not be vanishing if you add. Similarly, partial derivative of y is 0, right? If you take u equal to x cube, ux is 3x square, uxx is 6x, uy is 0, uyy is 0. If you add, you get 6x. It vanishes only at 0, right? But individually, x and x square are harmonic. X square, okay. Composition of two harmonic functions is not necessarily harmonic. Composition of two analytic functions is analytic, but composition of two harmonic functions is not necessarily harmonic. Similarly, inverse of or a square of a harmonic function need not be harmonic, and hence the class of a harmonic function need not be conformly invariant. What do you mean by that, right? If you have a harmonic function f, right, it need not map unit disk to conformally to any other domain. It need not map unit disk to conformally to any other domain, right? So what composition rules we can expect, or what are true if f is from omega, if f is a function from omega to c is analytic, and if g is from f of omega to c is harmonic, then g composite f is harmonic. You can understand why g is having domain as f of omega, because I need to define composition. If f from omega to c is harmonic, and if g from f of omega to c is analytic, then g composite f is not necessarily harmonic. If f from omega to c is harmonic, then nth power of f not necessarily harmonic. If f from omega is harmonic, inverse of f need not be harmonic necessarily. Now, in MSc, there is a famous result for analytic function, what is called Schwarz lemma, right? What does it tell? If f is an analytic function, the unit is delta, with f of 0, 0 and f dash of, and modulus of f of z less than or equal to 1 for each z in delta, then modulus of f of z less than or equal to z, and modulus of f dash of 0 less than or equal to 1, and equality attains in the cases which I have shown here, right? Especially when f of z equal to c z, where mod c equal to 1. Can you think of Schwarz lemma for harmonic univalent mapping, right? Can you think of Schwarz lemma for harmonic univalent? Right? Yeah. So to define that, I want to extend Schwarz lemma to harmonic mapping. So there is a notion of subordination, right? Subordinate, meaning what? Below, right? So a function f analytic in the open disk is said to be subordinate to an analytic function, univalent function. The second function I demand to be univalent g if number one f of 0 is 0 and f of delta should be contained in g of delta. The range of f of delta should go and sit inside the range of g of the range of delta under g, right? Symbolically we write that symbol f subordinate to g, right? And once f is subordinate to g, right, by Schwarz lemma I find that g inverse composition f is an right. If you apply Schwarz lemma to the function g inverse composition f, I get a function omega with the following properties: omega of 0 0 and mod omega less than 1, right? In other words, g inverse of composition f equal to omega. What do you mean by that? Bring the g this side. So f will be g composition omega. G inverse composition f of z equal to omega of z. So f of z will be g of omega of z. So whenever you have f subordinate to g, another way of looking at subordination is you can always get a function w with w of 0 0 and mod w less than 1, meaning it maps unit disk to unit disk, and f of z equal to g of omega z. This will be very much useful in some cases. To prove Schwarz lemma for harmonic univalent mappings, I need what is called Heinz lemma. Heinz lemma tells the following: if omega is set of all complex number such that modulus of real part of omega less than 1, and if f is a map from delta to omega with f of 0, 0, the delta is unit days, omega is the given set there, then the following inequalities are true. Modulus of real part of f of z less than or equal to 4 by 5 tan inverse mod z, and modulus of imaginary part of f of z less than or equal to the quantity showed here, right? And the inequalities are sharp, meaning for some f, equality will be true. That's the meaning of sharpness, right? An inequality is said to be sharp if there is some case, there is a case where equality holds. This is Schwarz lemma for harmonic mappings. A function f from delta to delta is harmonic if f of 0, 0, and the following inequalities hold, right? You can understand. Okay, we don't know. Now there is an interesting concept called Landau's theorem and Bloch's theorem. If anyone is taking a process, H can have first coefficient 1. Same thing we did for class S, right? This motivates us to define what is class SH. SH is extension of class S. We are extending class S, right? So S for analytic function, SH for harmonic function. The set of all complex valued sense preserving harmonic univalent functions. Complex valued harmonic sense preserving Jacobian greater than 0. Univalent functions on unit days with this condition f of 0, 0 and f is of 0 equal to 1 is called is the collection of the functions SH, right? Then H can be written like this, G can be, okay, already we saw that. What is SH naught? SH naught are those functions in SH where fz bar of 0 equal to 0, right? Fz bar, that means the first coefficient of G, B1 will be 0. Since B1 is 0, Taylor series of G will look like this. Summation n equal to 2 to infinity. Because B1 is 0, 2 to infinity Bn z power, right? So, SH and S0H are the main objects of study for harmonic univalent mapping. How S is the main object of study for analytic univalent mappings, SH and SH0 are two main objects for study of harmonic univalent mapping. And how are they related? The class S of univalent normalized analytic function is contained in the class SH not defined here, which is further contained in SH, which is also defined here, right? Please remember this inclusion. Every function in S is a function in SH not, and every function in SH not is a function in SH, right? I think I'll skip some. Okay. Normal family is a particular type of family of functions which have such that every sequence of it contains a subsequence which converges uniformly on every compact set on omega. And a normal family is said to be compact if every limit function is a member of that family. You know, convergence can take place, but the limit function can go outside the set. If I insist that it is also inside the family, I say it is compact family, right? And a family of harmonic function defined on omega is said to be locally uniformly bounded if I can find a, for every compact set of K, there is just a M depending on K such that mod f of z less than or equal to M for each f in F. This is a definition. You need this very important definition, locally uniformly bounded. And a family f of harmonic function is said to be uniformly, because of time I am running, right? If there exists absolute constant M such that mod f of z less than or equal to M. Actually, normal family, locally uniformly bounded family, and this family f of absolute uniformly bounded family are very much useful to prove, right, what is called Montel's theorem. Montel's theorem tells that a family of harmonic functions is locally bounded if and only if it is normal, right? So I gave the definition of locally boundedness, I gave the definition of normal family. How are they related? A family of functions is locally bounded if and only if it is normal. Examples of normal family: the family SH which we saw earlier is normal. The family S0H is normal and compact, right? These are two important results for theory case, for the case of theory, right? Now, you know, in 1916, I told you Beaverbach made a conjecture that mod I less than or equal to n for each function in S. Can we think similar to this for harmonic functions, right? So, coefficient problem class for the class S. Consider the class S consisting of univalent functions f defined on open unit disk with f of 0, 0 and f dash of 0, 1. Then functions will look like this. We all know z plus a to z square plus etc. Beaverbach proved himself that mod a2 less than or equal to 2 and equality occurs only for Kobe function. Then he conjectured further that for n greater than or equal to 3, mod n less than or equal to n. This was long standing from 1916 to 1984. 1916 to 1984, and it was proved by DeBranches in 84 and published as a paper in 85. Now, how will the conjecture look? Mod n less than or equal to n, which is finally settled, right? How will it look for harmonic universal mappings, right? Weber-Bach type conjecture for S naught H. Consider the class S naught H, F equal to H plus D bar. H is having this series shown here. H of z equal to z plus summation 2 to infinity a n z power n, and g of z equal to summation 2 to infinity b n z power n, right? The class is non-empty because the function shown here, which we call the harmonic analog of Kobe function, will be a member in S naught H. That you can check. The class S naught H is non-empty because the function k defined by H plus g bar, where H is given here and g is given here, will be a member in S naught H. Therefore, S naught H is non-empty, right? Then, if you expand this H as summation a n z power n, and that g is big H, okay, I'm sorry, and g as summation a b n z power n, then you see that a n will have the value 1 by 6 2n plus 1 n plus 1, b n will have the value 1 by 6 2n minus 1 n minus 1 for all n greater than or equal to n. A n minus b n will be n. This n is what you know, Weber-Bach conjecture coefficient. Mod n less than or equal to n for Kobe, analytic Kobe function, it is equal to n. And a n plus b n is 2n square plus 1. Now these things motivates us to a conjecture stated by Clooney Small, still open. Whoever is working in geometry function theory can take up this challenge, right? It is not yet proved, stated in 1984. How many years? You can understand, right? I think 40, no? Okay. If f equal to h plus g bar is S naught h, where h of z is z plus summation n equal to 1 to infinity a n z power n, and g of z is summation n equal to 2 to b n z power n, then each a n's in modulus is less than or equal to 1 by 6 2n plus 1 n plus 1, and mod b n less than or equal to 1 by 6 2n minus 1 n minus 1 for each n greater than or equal to 2, and modulus of mod n minus mod b n less than or equal to n greater than or equal to 2. This is still open. Nobody has proved it. Whereas they have defined, like the case of analytic case, several subclasses of SH has been proved. In fact, Clooney himself in his paper defines the analog of convex univalent harmonic mapping, close to convex univalent harmonic mapping, as in the case of analytic mapping, and proves the results, right? But for the whole class, it is open. It is open, it's a real challenge, right? As the Weber-Bach conjecture stood from 1916 to 84, this is from 1984, it is still unproved, right? And similarly, conjecture 2, let f equal to h plus g bar be belong to SH. Understand the difference? This is here S naught H, where f z bar is 0, right? When it is in SH, right? If h of z is having this series and g of z is having this series, then mod n less than or equal to 2n square plus 1 by 3 and mod bn less than or equal to 2n square plus 1 by 3. The bounds are sharp, meaning there is a function for which the inequality become equality, but still we cannot find that function. We are unable to find, right? So apart from that, there are variety of problems in harmonic univalent functions. Just type in Google harmonic univalent mappings, you will get so many research papers, so much research is going on. There are several topics. Due to want of time, though my topic was on some theory and problems, I didn't have time to prepare problems. But there are so many problems which you can work on if you are really interested in harmonic univalent mappings. Nearly 10 to 15 topics will be there. Right. These are the references from which whatever I talked here is available in this. Clooney and Small, the first paper on harmonic univalent mappings, published in Annals of Academic Sciences, right, 1984. There's a classic textbook for harmonic univalent mapping by Peter Duran. I don't think soft copy is available for this, right? But the other one soft copy is available. Analytic univalent mapping, but the soft copy is not available. The full set is not available. It costs around 8,000 or something. And the entire presentation was based on an article by Ponnusamy and Priscilla, Planar Harmonic Mapping and Quasi-Regular Mappings, published in Computation Methods in Function Theory, RMS Lecture Notes 19, published in 2013. Any questions? I think I had to hurry up because of want of time. A lot of openings are there in harmonic univalent mappings. It's a good area for research. Any questions? Thank you.
Thank you for a wonderful speech, sir. Now I welcome the dignitaries to occupy the stage.
Hey. ஆமா ஆமாண்டா யூடியூப்ல தான்டா போயிட்டு இருக்கு ஆமா
We will now have the valedictory session of today's event. I would like to call upon N. Purnima Ma'am, Assistant Professor, Department of Maths with CA, to give a brief report on today's seminar.
Good evening. Hello. Respected dignitaries, distinguished speakers.